So it's a second day, and we start with the first session of the day. We have here already our next speaker, that as for the other next speakers that we have, for all the speakers that we have during the school, doesn't need any specific introduction, because I mean we all know him, but just let me give him a brief introduction of Avik Bhattacharya. Welcome, Avik. Avik received the Integrated Master of Science degree in Mathematics from the Indian Institute of Technology in Kharagpur in India in 2000, and the Ph.D. degree in Remote Sensing, Image Processing and Analysis from Télécom ParisTech in Paris, in France, and the Ariana Research Group, Institut National de Recherche and Informatique and Automatique in INRIA, Sophia Antipolis in Nice, France in 2007. He is currently an associate professor at the Center of Studies in Resources Engineering at the Indian Institute of Technology Bombay in Mumbai, India. Before joining IITB, he was a Canadian Government Research Fellow at the Canadian Center for Remote Sensing in Ottawa, Canada. He received the Natural Science and Engineering Research Council of Canada prestigious visiting scientist fellowship at the Canadian National Laboratories from 2008 to 2011. His current research interests include SAR polarimetry, statistical analysis of polarimetric SAR images, applications of radar remote sensing in agriculture, cryosphere, urban, and planetary studies. You can find his complete bio in the document that we have sent to you for the introduction of our speakers and the school. So let me stop sharing my screen now, and without further ado, I just give the floor to Avik for this second session, second day of our school. That, as we said, it's pretty organic with the last contribution that we had yesterday from Carlos Lopez Martinez. So thank you, Avik, and I look forward to hear your talk.
Thank you, Andrea, for the introduction, and thank you for you, Maria, Salwa, and all others for organizing this winter fall school. And I would like to take this opportunity to thank Professor Paulo Gamba, our president of GRSS, for his support and encouragement throughout having it. And it is my pleasure to be a part of this event. And without ado, I just share my screen. Okay, so I think it's visible. Okay, thank you. So welcome to this presentation, which is titled as Applied Mathematics for SAR and PolSAR Information Extraction. First of all, before beginning this presentation, I would like to thank Professor Lopez Martinez, who introduced this subject with many, many more beautiful things yesterday. And I'm sure you've learned a lot about it. In this presentation, I will be only focusing mostly on the PolSAR part of it, the information extraction from PolSAR data. And as it says, it will be mostly well, applied mathematics, but we'll be mostly talking about the tools and the techniques which are required for many different applications. And we'll just talk about also the theory and the applications. So the lecture topics will be first of all, we'll just try to look into the data representation of PolSAR data, which is important to start with, because without that you cannot move ahead. So we'll just briefly talk about the data representation. We'll talk about the target decomposition concepts. Well, not of course all of them. It's not possible within the scope of time over here, but we'll just talk about a few of them and talk about the basic principles behind them. I'll take you through another concept, which is unified framework concept for data analysis in PolSAR data, which is pretty new in this field, but it's very powerful, and it's very nice to look into the things. After that, we'll talk about the target characterization using some model-free approaches. And at the end, we will look into some applications with the user utilizing various novel descriptors, which we'll be talking about in the other 4 parts of this. We'll be utilizing those novel descriptors for some applications for Earth observations. Since this is in total the topics, I've divided into it in part 1 and part 2 because this is quite a long. So let's begin with the part 1 is the SAR PolSAR data representation. So as you have already seen in yesterday's lecture, I'll just start from there. So what you have is you describe the scattering matrix, which describe the dependence on the incident and the scattered Jones vector. And what it contains the information about the change in the polarization between the scattered EM wave. And this depends on many different things of the scatterer shape, material, which is in terms of the dielectric properties, the EM wave frequency, the geometry of the target, and the local coordinate system. So this is what is the starting point. You have the measurement of the scattering matrix. What you have is you can have those. It's a 2x2 matrix. Each on elements is a complex matrix which has a magnitude and a phase, and you have the absolute scattering matrix written in this form, where you have the magnitude and the phase. You can write them in terms of a relative scattering matrix, where you can take, without any loss of generality, you can take a phase out, and you can then have phase differences. And then you have, in general, have 7 parameters, which are 4 amplitudes and 3 phases. This is in general. What happens, you have the coordinate system in X and Y, the Cartesian system, but you can also have it, you can just replace that with an HV coordinate system. So then it becomes the horizontal and the vertical polarization basis system. In the case of monostatic backscattering case, where you have the principle of reciprocity holds, you have the SHV is equal to VH. And in that case, you can write the same scattering matrix in this form, again in terms of the amplitude and the phases. And then you are left now with 2 parameters. Less, we have now 5 parameters, where you can have 3 amplitude and 2 phases. So this is the basic representation of PolSAR data in terms of scattering matrix. Now, different kind of scattering which we have. We have coherent and incoherent. So how do we characterize them? When we have coherent scattering, then it is completely polarized wave. Then the 2x2 matrix is enough to characterize those kind of target scattering. But in nature, everything is partially polarized. So a scattering matrix will not be sufficient enough to do that. So you need a statistical description of that. So the thing is, if you have a completely polarized, S is okay, and then you have an incoherent one, you need a statistical description. How do we do that? So we have a scattering matrix, which is, again, as I mentioned, a 2x2 complex matrix. The column of them are the wave polarimetric information. Have the Hs and the HV and the VH, and you form a scattering vector out of it, the vectorization of the matrix using some basis element. And from there, you can find out 2 covariance structure. But just to differentiate them, we write them to be as a coherency matrix and the covariance matrix, just depending upon the different basis matrices which are used for that. So you go from a coherent target, you can represent an incoherent target by taking this ensemble averaging process. But there is another representation which is also very beautiful, is the real representation, which is the Kano representation, which can also be represented for both coherent and incoherent targets. So in all, we have the polarimetric data representation in terms of the coherency matrix, the covariance matrix, and the real Kano matrix. How are they related? They are related by just a transformation symbol. You can go from the T to C, C to K, and from T to C and K to C, where the red line says that you cannot come back from K or C or T to the S because you have already have an ensemble average done, so you cannot come back to it. But otherwise, you can go from one to the other by the simple transformation. So this is, in nutshell, the representation of PolSAR data. Let's go on to the next one, which is the PolSAR decomposition target, PolSAR decomposition concepts. So in general, radar polarimetry, as I like it very much, it deals with physics, statistics, and geometry. You have looked into some of the physical aspects, the physical behavior of scattering from yesterday's talk. You will look into the other part, which is involved for the statistics part of it, the information geometry, into the next talk after my talk. And there is also the geometry, which also combines them. In one case, we can have polarization geometry. In another case, we can have the information geometry. So this is how, in a nutshell, everything is like combined and they represent in this form. The PolSAR target decomposition concepts is in this form. So you have measurements, which are the S matrix measurements. You can go from there to the T or the C. This is again the rank 1 matrices. What you do an ensemble averaging of this, and you get a distributed or an average target. So something like this is what you start with. But let's start with what we have in the literature, the PolSAR decompositions. The group of decompositions which utilizes the S matrix are the one which are the coherent decompositions. There are a couple of them in this, Pauli, the Krogager, Camaro, and there are other few of them. If you go to the one which involves or utilizes the coherency matrix, the Canot matrix, or the covariance matrix, you can have either the eigenvector-based decompositions, or you can have the model-based decomposition. In between them, there is also another variety which also is the target dichotomy. So in this talk, we will talk about a little bit about some of them, because we cannot cover all of them. We'll talk about a few of them in this talk. There is another one which is utilizing the compact polarimetric SAR data, and nowadays the sensors are equipped with acquisition of compact polarimetric SAR data, and there are a couple of decomposition which utilizes the compact polarimetric SAR data. But this we'll not be able to talk in this part of the lecture. Let's go into the coherent decomposition, which utilizes the S matrix. So what is the principle behind it? Principle is very simple. We describe the measured S matrix as a combination from different simpler canonical targets. So we assume that the desirable property, assume that they are independent. That means we do not have one matrix with the other overlapping in any terms of information content, and we try to have a restrictive property of orthogonality in them, that they are measuring, interpreting one scattering phenomena by itself. In this regard, we have the simple one, which is very, very simple to do as the Pauli decomposition. You can decompose this S matrix in terms of the Pauli matrix, basis matrices, in terms of an odd, even bounds at 0 degrees, which is orthogonal, or in even bounds, the dihedral rotated at a 45 degrees to the radar line of sight, or you can have an completely asymmetric components. So you can break it up very clearly, where A, B, C, D are complex quantities. And if you break it up, you get A is A, B, C in this form. So this is a simple way of just decomposing or breaking up a 2x2 complex matrix in this form. In the case of monostatic case, which we will be dealing with throughout this course, is that you have reciprocity. You have HV is equal to VH, which then implies the last quantity D to be 0. And you talked about the span, so the total power is nothing but the intensity, the sum of the intensities of all of them is equal to the mod of A squared plus mod of B squared plus C squared. So this is how you simply can break it up into the Pauli decomposition. It's very useful because when you have a PolSAR image, what you look into, the first thing is what you say as a Pauli image, a false color composite. And how we make the false color composite is we just take these elements and form the intensity out of them, that is the mod of them square, and we put them into the RGB channel. And that's what makes the very first impression of a polarimetric SAR image, a false color composite. So simple but useful is the first step. Next one is from the cryo decomposition with sphere, diplane, and the helix, the SDH. You break it up into three components in sphere, a diplane, and an helix. And we can break it up in the S in terms of the sphere, diplane, and helix. And I put them in a circular basis component, which is easier to put and easier to understand in the RL basis, the right circular and the left circular basis. And you see it can be break it up into the sphere component, the diplane component, the helix, and in front of them you have the KS, KD, KH, which are the components which are characterized by those scattering matrices over here. You can find out the KS, KD, KH, very simple way. You can have the phase, the absolute phase, which is taken outside, which is not required as such in PolSAR. You have the orientation angle, theta, the orientation of the dihedral along the radar line of sight, and you have the phi s, which is the displacement or phase of the sphere with respect to the diplane. But you can see over here, you cannot actually have this same information, the displacement of the diplane with respect to the helix, because of the fact that the sphere and the diplane are mutually orthogonal, and the sphere and the helix are also mutually orthogonal, but the diplane and the helix are not mutually orthogonal. So this is very, very important to understand. That means you can form the helix by a complex combination of 2 or 3 more diplanes in a resolution cell. So that's how you get this Kruger decomposition, also very nice and useful. The next one comes in the Cameron decomposition. Here, Cameron introduced a target which is called as a symmetric target. The idea is to break the S matrix into something as a reciprocal and a non-reciprocal, and the reciprocal is then further divided into symmetric maximum and minimum. So what you do is you have the S matrix vectorized, and then you can you can decompose them in terms of a symmetric component and an asymmetric component over here. And you have the theta RC, which corresponds to the degree of scattering, which obey the reciprocity theorem, and if for 0, it is strictly reciprocal. If it is pi by 2, it is strictly non-reciprocal. And you have the tau, which then segregates these reciprocal into maximum symmetric and strictly symmetric and strictly asymmetric component. This is how the Cameron decomposition is, but you can also utilize it in a very elegant way. You can also utilize those parameter, and you can do a scattering matrix classification. So you can utilize those to break it up into reciprocal and non-reciprocal targets. You can do a test of symmetry, and you can then see match with the helix component. If you match it, you have the right and the left helix, and then you can also match it with a distance measure with different kinds of canonical targets, which are trihedral, dihedral, dipole, cylinder, narrow dihedral, and so on. And depending upon that, you can assign them to either one of them. And if you do not have the distance measure characterizing those targets, then you would say it's a general symmetric scattering. It's a nice way of looking into the scattering matrix decomposition in this term. So as you can see that you can actually decompose the S matrix in different formats. There is no unique way of doing it. So it means without any a priori information of the scattering, it is non-unique in nature. There are different ways in which you can do that. Also, as you have seen in your previous lecture, is that they are affected by a phenomena called speckle. So speckle plays an important role, and it's also, so it is very useful when you have scatterer or images which are very high resolution, low in entropy, and you would like to characterize only maybe one single type of scattering in your target, so in your scene. So in that case, it is not useful. Otherwise, you have to be very, very careful when you are utilizing the coherent decomposition. The next set of them is the eigenvalue decomposition and the model-based decomposition, which utilizes the T-C matrices. So, as I said, the incoherent decomposition principles is that I first have the S matrix, of course, the first measurement for the pure target. We go to the T and the C, which is the distributed target over here. And we have several ways of doing the incoherent decomposition. The first one is the model-based decomposition. What you're trying to do, you're trying to fit the model to your data. You have a mathematical sense of doing it. You are doing it in terms of the eigenvector and the eigenvalues decomposition. So these two are there in literature. Then another one, which is what we do in terms of factorization. So it's the scattering power factorization. We'll look into that in more detail. And the next one is we have something which is model free. So we are not bothered about the model anymore, but we are trying to do the decomposition over here, but without any relevance to any kind of a scattering model as such. So the first one will be the model-based decomposition. So let us try to see the first approach, which was given by Freeman and Durden in 1996, which is a three-component one. So you're fitting the C or the T. I'll just talk in terms of the T, but you can do it for any one of them. So the T matrix, what you're trying to do is you're trying to fit three different scattering models into the data. So the surface, the dihedral, and the volumetric. Something which is the odd bounds, in general the even bounds, and the random scattering, the volume. And this is how you try to fit into, and you try to do the inversion and solve it in terms of, and you try to get the powers associated with them. The PS, the PD, and the PV are the powers associated with each of the components. It assumes, these decompositions assumes a symmetry, which is the reflection symmetry. And this is maybe is possible when you have a kind of a homogeneous natural target, but for other target, this might not hold. These parameters over here, you can see the T is in terms of parameter beta and alpha, where these are the modulus of them are less than 1, and this is a function of the Bragg's reflection coefficient, the ratio of the Bragg reflection coefficient, so on. This is the simplest one to start with. The Freeman model-based decomposition with three components is very useful, and it gives you a first impression of how it looks like. This is an image of the San Francisco area for the SAR data, and you can see by looking into the components and a false color composite into a PD, PS, and a PV, you are able to make out quite well the first impression about where it have the water surface, where you have the urban areas possibly, and where you have some of the vegetation. The next one came in 2005 around with Yamaguchi, the four-component decomposition with an introduction of the helix component. Here, the assumption of the reflection symmetry is not utilized. So here we have a non-reflection symmetry condition, and you introduce a parameter which is helix. And as we have seen before, this helix component was utilized first by Krugager in his coherent decomposition. So the idea is that we have the same other three components remaining the same, but we have introduced another one, which is the helix. What more, we have also now over here the volume component, which is also divided in terms of the ratio between the copole channels. So we have the two asymmetric one and the one as the one same thing as was used by Freeman. This corresponds to the condition or the volumes which can come from natural targets which have some orientation and so on. So this is three different volume components has been taken with some criteria depending upon the ratio of the copole channels. And utilizing them, we can get the image look something like this. Of course, if you compare, it looks slightly better than the three-component decomposition because of the fact that here we have introduced the concept of non-reflection symmetry. So you have the PC component coming in, and also the fact that you have introduced the volume component in a different way. So not the volume component which was used in Freeman as the random cloud of dipoles, but here you have specified a distribution of the dipole depending upon certain physics of scattering. So this is how It looks like the three component, the four component decomposition, but here I have put just the three component for the sake of visualization and comparison with the Freeman-Durden decomposition. The next one was an improvement over the Yamaguchi four component decomposition because of the fact that the volume is of course is there because of the random scattering from vegetation or from natural targets, but it also can happen from targets which are rotated above the radar line of sight. So the T33 component, which is used in the volume scattering component as a volume scattering component, this T33 we can result also in from targets which happens in oriented urban area, oriented to the radar line of sight, that can also give rise to the HV component. So the idea was that can we do a rotation, a unitary rotation of the initial coherency matrix, you rotate by a unitary matrix, and then you perform the differentiate the T33 component and make it to 0. That means you're minimizing the T33 component, and when you do that, you obtain the theta, which minimizes the T3 component. And that theta you use to rotate it. So once you rotate it, you get the rotated T33 minimized coherency matrix, and then you do the same formulation again. You again break it up into the four components of surface, dihedral, volume, and helix, and that is utilized, and it is not called the Y4R, the Yamaguchi for component rotated. It happens in areas where you have urban areas which are oriented to the radar line of sight. So if you see that, it's better than the one before. You are able to capture more information from the urban area, which were otherwise not able to be captured in the previous two decomposition, the Freeman-3 component decomposition and the Y4O, because of the fact that this rotation thing was not done over here, and with this rotation formulation over here, we are able to get more information from the urban area, which possibly are rotated to the radar line of sight. So just to give a direct comparison of the three of them, you can see that you have clearly a nice way of analyzing that the three component, even if it is simple, very straightforward to use, it gives you a very nice information, the first hand information about the type of scattering, a modification of that in the Y4O, introducing the non-reflection symmetry and the volume scattering component, which is also modified. You get slightly better in the urban area, and utilizing the Y4R, you are able to get quite a lot of improvement in the urban area. So that's how you get in the composition has been, we're able to increase the amount of information content in those areas from the FDD, the Y4 and Y4O and the Y4R. Next, going on to the next incoherent decomposition is the eigenvalue, eigenvector based decomposition. It's again to understand over here is that we have the S matrix over here. The same thing as we have discussed before. We have the S matrix, we vectorize it to a scattering matrix using the Pauli basis, which looks something like that. You get the Pauli basis scattering vector, and then utilizing, you form the outer product of that and do an ensemble averaging over them. What you get is a T matrix. Then you just decompose this T matrix into an eigen decomposition where you have the unitary matrix and S coming from the SU3, and you have the diagonal the diagonal matrix, which is the real eigenvalues over here. So the columns are nothing but the orthogonal eigenvectors, and you also have the real eigenvalues. So this matrix is by mere construction is a Hermitian and positive semi-definite. So this is a nice way of again decomposing this T matrix, because you're able to have orthogonal eigenvectors and you have the real eigenvalues. What can we do from them? So the idea is that utilizing them, we can parameterize the eigenvector. So you parameterize in this way. So you have the angles and something like phases over here, and you are able to put them into a form where you have the parameterization of the column vector for each one of them. So what we do, we need to then go on to find out the probabilities. In this case, they are called as a pseudo probabilities. They are not actually the probability measure, but you can always find out the probability measure by just dividing this lambda by the summation of lambda, where the summation of all the PIs is equal to 1. And then you can form the average parameters, because here in the previous slide, as you have seen, you can have 3 targets over here. But instead of that, you can form an average target over here by finding out an average alpha, which is nothing but just a sum with weighted over the probabilities with all the parameters, the alpha, beta, delta, and the gamma. And then you can find out the mean target, which is nothing but U naught, which is the mean target characterized by this. So this is how you form the eigenvector decomposition. So first you do the eigen decomposition of them, parameterize them, and form the probabilities out of the eigenvalues, and then you utilize them to form the average parameter, and that's what you utilize as a means scattering mechanism. There's another very important property which is called the roll invariance property. What it says is simply that the effect of rotation around the radar line of sight. So that means, do I have it or do I not have it? So this is the property what it is. So what I try to do is that I rotate this T matrix. This is what you have seen before also. I rotate this T matrix with a unitary matrix around the radar line of sight. This is purely geometrical. And I see that the eigenvalues are roll invariant. They do not depend upon this roll, this angle, which is the orientation of the radar line of sight. And I see that if I do that, then I have these alpha parameters over here are also roll invariant. And also that means the average parameters, which means that since the P's are calculated from the lambdas, which are themselves roll invariant, P's are also roll invariant. The alphas over here can be seen, just simple calculation. You just do simple calculation and you see these alphas are also roll invariant, whether others are not. The beta, delta, gammas are not. So if I utilize them to find out this average quantity, then this average quantity, average alpha, is roll invariant also. So it's very interesting to see that I have the roll invariant parameters in terms of the lambdas, and also this parameter, this nice parameters lambda, I just lambda under bar something and say, which is also roll invariant. What does it characterize, this alpha? It characterizes the scattering type information. 0 corresponds to 1, which are something like an odd single bound scattering, and the other extremities over them is a 90-degree, which corresponds to dihedral scattering, pure dihedral scattering, and this is a kind of a pure surface scattering, pure odd bound scattering kind of, and between it's a continuous scale. So you can see that this area, which is this San Francisco area over here, consists over here of urban areas. This is an area where you have water bodies, and of course some areas which is covered with some vegetation. If you can see, you are able to get something over here around 60-degree or so, which corresponds to the area where you have urban area, but this urban, since it is mixed with other kind of scattering, so it's a mixed scattering, you do not have anything over here as pure kind of a dihedral, but it's a mixed over here. You're able to get scattering over here towards this in this scale. Wherever you have water body over here, you are able to characterize it somewhere over here. And in between, if you have this mixture of mixed scattering over here coming from forest or some kind of vegetation over here, you are somewhere over here. So this actually again gives you the information about the type of scattering over here with this alpha parameter. So this is again a beautiful parameter to analyze in SAR polarimetry. What more you can do? You can find out the degree of randomness, what is called as the polarimetric entropy, which measures, of course, the statistical disorder. and you can measure it with the entropy. This is the von Neumann type of entropy. If you have utilized the P1 is coming from a pseudo probabilities measure of the eigenvalues, and this gives you information about the randomness, the polarimetric entropy. For a pure target, of course, the entropy is 0. So that means you have only the total energy, the total information, total power is carried only in the first component of the lambda, others have nothing. This is totally a system where you don't have any disorder as such. The next one is a distributed target, where you have a case where you can have all the lambdas are equal, which is equal to span by 3. Then you have the entropy, which is equal to 1 total disorder. So you will be able to measure the amount or the degree of randomness over here. And you can see an image out of it. If you see the same image, you see the entropy, you're able to see that the water body, which is more or less purer, of course, over you can see it's very, very low. The entropy is very, very low, more purer over here. If you go into the vegetation areas over here, which has more of random scattering over here, randomness as increased over here, you get entropy close to 1. In between the urban area, which was mixed of dihedral and some other kind of scattering, it's not as high or it's not as low, it's somewhere in between. So you're able to characterize with the polarimetric entropy these scattering type information and the scattering randomness information. And these two parameters have been nicely used in literature to segment scatterings given from a scene in a 2D plane, the entropy alpha plane. This is a nice segmentation, and you can see that without any a priori knowledge, you don't do anything at all, but just put those where they fall into this plane, and you're able to segment the scene into 8 different clusters. The 9th one over here is invisible, and this has a mathematical basis. You can see that. So this corresponds to a low entropy, a medium, and a high entropy region, and you have alpha from very low to very high. In between, you have the dipole scattering over here. So you can see that I'm able to characterize this all the scattering given in a scene with the two very useful and very nice parameters, the alpha and the average alpha and the entropy. So I am able to segment them like this. Given an image, I can segment them with this is just the occurrence of the point in the H alpha. You can see where they fall into. The intensities are given in terms of the red are more intense and the blues are the less intense. This is the occurrence point. And if you just segment them in terms of the clusters, and you can separate them into 8 different clusters. So this is a very, very nice and a very informative way of doing a clustering of a scene without using any a priori knowledge. And it's very, very useful to start with to understand a polarimetric scene. There's another parameter which is very important, which is called the scattering anisotropy parameter, defined by just the difference between the second and the third eigenvalues. This is important and this is complementary to the entropy, because it is very useful when you have entropy greater than 0.7, which it's higher entropy, as you can say, because for lower entropy you may have the eigenvalues, the second and the third eigenvalues be noisy, and so the entropy anisotropy parameter won't make any sense. But for high entropy, this makes sense, and it is very useful to discriminate. Even if you have a higher entropy, you can again say that there is a second or a third mechanism happening over there in the scattering. This parameter, as the other two, the alpha, the average alpha, and the entropy, is also role invariant. What's important to see over here is that you can say that for a higher entropy, I am able to say that there is a way you can segregate out the differences with the anisotropy. The anisotropy can be 0, but it can also be high, or given what way the lambda 2 and the lambda 3 are distributed. If you see simplistic way, you can just decompose the span utilizing these two parameters, which are eigenvalue based, the entropy and anisotropy, which corresponds to 1 scattering mechanism, 2 scattering mechanism, and 3 scattering mechanism, depending upon how your H and A behaves, high or a low kind of thing. So you are able to decompose the span into these 4 ways. That means if I have the characterization parameter, the scattering type, the alpha, which characterizes the type, and this entropy and an anisotropy in combination of them. I have those which characterizes kind of the discriminate the span into different kinds of scattering. Here in terms of 1, 2, or 3 scattering mechanism, I will be able to utilize them in any other methods to cluster a polarimetric SAR image. An anisotropy image looks something like that. If you have somewhere over here is anisotropy is very low, even if the entropy is very high, but at some places where you have entropy to be high, you can have anisotropy also to be very high, which can characterize that there, even though the entropy is very high, you can also characterize 2 mechanisms over there. So this is how you characterize with the 3 parameters, the H, A, and the alpha. So this was the 2 parts which we discussed about the data representation of PolSAR and some very preliminaries of PolSAR target decomposition concepts, which has been utilized a lot in the literature, and there are many more which are there. So I just briefly touched upon the very basic principles about them. I'll go to something very new, which is a unified framework for PolSAR data representation. And this is a very nice way. So that means the idea is that there are geometrical analysis of PolSAR data is very important because they form a geometry. So what I could do is that I can form a kind of a distance measure between 2 Kano matrices. I'm dealing over here with Kano, but this can be extended to covariance and coherency matrix alike. Not a problem at all. But just to give an over here, we are trying to deal with the real representation. So here we are just a given representation in terms of the Kano matrix. So the geodesic distance between the 2 Kano matrices is given in terms of this expression, which is nothing but just a trace operation, as you can see. And this has very nice properties over there, that is scale invariant and also invariant under orthogonal transformations over here. And this can be utilized for different kinds of characterization of our polarimetric SAR data. What we are doing over here, we are just trying to utilize the nature of the geometry between distances between 2 observations over here, or the geodesic distance between the observation and some of the canonical targets which are there in nature. So utilizing this concept, we can do a lot of things which has been done prior to this study, which can also be mapped into this utilizing the geometrical nature of polarimetric SAR data. So in this respect, I will talk about 3 different aspects of this. I will be talking about some of the role invariant scattering type descriptor. I'll be talking about a power factorization framework, and we'll be talking about some applications. So what are these 3? So this one, the first one is role invariant scattering type descriptors. What you have seen just now before is I was talking about role invariant scattering type parameters, the alpha bar, or the average alpha from cloud and Fourier decomposition. You have also seen the entropy, which characterizes the scattering entropy, the polarimetric entropy. You have seen the anisotropy parameter also, which is role invariant. So these parameters are role invariant parameters, which are very useful in understanding the scattering mechanism. The same idea, can I also utilize them within the concept of a geodesic distance between the Kano matrices? And that's the idea over here. I'm trying to bring the same thing, the same philosophy from there, but trying to understand it in a more geometrical way, in a more physical aspect. So the idea is that utilizing them, I'm trying to find over here some role invariant descriptor, similar to the one which we can have from the eigenvalues, eigenvector based decomposition. But at the same time, can I also utilize the same unified framework concept to get the powers? Because as you have seen, we have distinguished between the eigenvector based decomposition and the model based decomposition. The model based decompositions are characterized by powers. They are there are scattering powers which characterizes the scene. In terms of eigenvalue, eigenvector based decomposition, there are role invariant scattering descriptors which characterizes the scene. Here, I'm trying to bring them under the same umbrella, the same framework. I'm trying to get invariant parameters utilizing the same geometrical aspect, but also going ahead, I'm also trying to find out the power information, which is over here is in terms of a factorization framework. So this is what I'll be talking about in this part of the talk. And then we'll see some of the applications for Earth observation. So the scattering type, as you have seen before from the cloud alpha scattering type, we also define a scattering type as the alpha GD, which is defined in terms of the geodesic distance between the observed kinematrix and the kinematrix for a trihedron. Since this geodesic distance is a quantity, which as we have seen before, is quantity between 0 and 1, we have just multiplied 90 to be in the same scale as we have it for the alpha from the cloud, which is also between 0 and 90. So 0 corresponds to the case when we have targets which are trihedral, that means single scattering or odd bound scattering. Here also the geodesic distance between a trihedral and trihedral would be a 0 over here, and this corresponds to 0. And over the extremities will be the dihedral. So if you try to see over here, this is how the targets are. A trihedral is given by 1, 0, 0, 0, 1. So these are the rows. Be careful. You can see over here, these are the rows over here. And you can see that this is correspond to a trihedral over here. So if you are trying to find out this information, so that means the alpha GD, the scattering type information, is between the observed and the trihedral. So what I have is over here. So between the trihedral and trihedral, of course, the GD is 0, and you have the alpha GD to be 0. But between between a dihedral and a trihedral, it will be 1. GD is 1, and you have the alpha GD to be 90. So it varies from 0 to 90 again in the same scale as you have seen before. With the helices, which are the asymmetric targets over here, the left helix and the right helix, you also see you have it to be 90. So here you have a problem, and this is also there. You can see this is also the issue when you also utilize the alpha from cloud and Potier, that it is unable to distinguish between, in a resolution cell, you have a dihedral and helices. The same thing happens over here. So, but we are able to distinguish between other targets. So this is the scattering type information. How does it look like? If you see, as we have seen that before, the alpha bar, which is the cloud alpha, and this is what we have in our alpha GD. So if you can see that it characterizes similar targets over here, urban area, and also over here the thing, but you can see that the contrast is much more higher, and would say better in some cases over here, in order to understand the differences between them. So you're able to characterize the target in a similar way as alpha, but it comes from a totally different kinds of concept over here. This is the area of San Francisco. For a C-band data, this is from an ALOS 2 data, the same scene over here. You're able to characterize over here the alpha bar, which characterizes again the scattering type information, and this is the alpha GD, which characterizes similar over here the alpha, but you can see you're able to characterize the urban area slightly better than over here. So this is this, but it gives you similar kind of information over here. This is the area from Mumbai, from where I come from. This is the Mumbai region, the entire Mumbai area, and this is the outskirts, suburb of Mumbai. This is the main Mumbai area, the entire. I come from somewhere, just to give an idea of where I come from. You can see the lakes somewhere in between over here. So this is the Mumbai region. You can see it's heavily urbanized area, and you can see the same thing which can be characterized by the alpha parameter over here, the alpha bar from cloud, and the alpha GD parameter, which can characterize very clearly the urban area, which is over here on the higher side over here on the alpha scale, and the the area which corresponds to the C, or kind of a single bounce or an odd bounce scattering, corresponds to the one which is towards that 0° over here. So it's able to characterize nicely the scattering behavior from different targets. I go to another case where I have an image which is from a mountain area. It is the Himalayas over here from India, the area of Manali Dhundi in area, which is snow-covered area. This is an image of an air from the time when it was snow-covered, and you are able to see that these are the high peaks. So it is increasing over here, the altitude, and you can see that this area where there are snow-capped areas over here, you are able to see scattering which is coming from a mixture of course over here from so around 50 to 60° over here is a mixture over here. This is something like a drier snow kind of thing. So it's a mixture of different volumetric kind of scattering, and also some of the dihedrals also over here because of the geometry. And you can see over here, same thing can be characterized over here from the alpha GD. This area is a forest which is frozen, of course, at that time of the year. This is something at the time of March, I would guess. In India, and this is a forest which is kind of a frozen, not a very dense forest, sparsely a dense forest, and you can see it over here characterizes something over here as a surface kind of a scattering over here, and the areas over here correspond to something like a mixed volume scattering over here. So we are able to characterize again different kinds of scattering from different kinds of targets and different kinds of areas, as I've shown, and compared it with the alpha of cloud and Poitiers over here. And in a nutshell, they show similar behavior. Also, the alpha GD is able to have a better contrast in terms of the targets, differentiating the targets. But as you have seen before, that we are unable to characterize the resolution cell if we have a dihedral and the helices, the right and the left. So we go on to find out another role invariant parameter, which is the scattering helicity. So which utilizes the helix component, as the name suggests. So it is nothing but you have a geometric mean between the geodesic distance between a left and a right helix over here, and then you have the 45 multiplied, because we will compare it with another parameter, which is the helicity given in the work of Tuzi, where we will be comparing that alongside the parameter given by Tuzi in his decomposition, the helicity parameter. So in order to have a comparison, we again have multiplied it 45. Otherwise, this again varies from 0 to 1. If you see again over here, this is the same thing as I've shown before. You can see the left and the right helix corresponds to the Kenu matrix in this way. But now, if you see, we are able to, utilizing the helicity, we're able to have a distinguish between the dihedral over here and the helix. So that means if it is a perfect helix, my tau GD is 45. Otherwise, if it is the extreme one of a trihedral, this is 0. So that means alpha is not able to characterize like the cloud Poitiers. Alpha is not able to characterize the resolution cell between a dihedral and the helices. That's why we need to bring into an helicity parameter, which then can do the job of differentiating it. Just to show an image over here, since the helicity, of course, is very, very low always in many of the areas. So you can see that I have just kept the entire range over here from 0 to 45, but you can see the values are very, very low. So we have compared that with the tau M1 of obtained from the Tuzi decomposition, and you're able to see that they are well, they have differences, of course, in terms of these information, but you can see that the information content is different, but just that they have a different scaling approaches over there. So you are able to get information about similar images. You're able to get information about the helicity component if they are present. So they will be only present in some of the urban areas and so on, but otherwise over homogeneous vegetation areas, they would vanish as such. So I'm still able to capture the similar information which is present in the tau M1 with my tau GD. for different areas. This is again the area of Mumbai. You can see it is fairly higher over the area where you have the urban area from Mumbai region. And also the similar thing happens when you have the area which is comprised of a snow-capped area. So the area which have the volume scattering coming from the snow, uh, the snow volume comprised of that, you are able to get some information about the scattering, which corresponds to some of the helicity component, some kind of an asymmetry in the scattering. So what we have seen that we have utilized one parameter which characterizes the scattering type parameter, which is the alpha GD, which is equivalent to the cloud Portier alpha, the average alpha. You are able to get similar information, but we are able to have a different contrast in characterizing the surface and of course the dihedral. So you're able to get a bit more contrast in. We are also able to utilize the scattering helicity type parameter, which we are then able to utilize it to distinguish between a dihedral and the two helices in a resolution cell. The next parameter, as we have seen before, is the polarimetric entropy, which you have seen, which characterizes the randomness in the scattering. So can we also utilize the concept of the geodesic distance between targets to find out a similar kind of thing, not the same, but similar kind of an information. And that's where we come to something, we call it as a scattering purity, defined in terms of something like that, a geodesic distance between a observed kinematrix and a perfect depolarizer. Now, how this comes into picture? We have a parameter which is given as a purity parameter, which is given as a called as a parameter of depolarization. The polarization was given by Gilles and Barnaby in 85 in terms of, again, the same way as a trace between the kinematrices. And they utilize as a depolarizer in order to give the same information. So it's nothing but kind of a norm between the distances, the normalized kinematrix. So utilizing the similar kind of idea, we also have provided the geodesic distance between the kinematrix, our kinematrix, and the depolarizer. But as we can see that if you take any of the canonical targets, the maximum it can go to a depolarizer, because nothing is depolarizer in nature. So we can just say that the maximum it goes from 0 to 2 by 3. And so in order to make the PGD vary from 0 to 1, we just multiply it by 3 by 2 over here. And we square it just to have a bit more contrast between the lower and the upper values. That's it. So if you see that it has an origin which is coming from literature, but we have utilized the geodesic distance over the framework is the geodesic distance, but we have utilized the depolarizer. So if you see again that the PGD is 0 if you have an ideal depolarizer, and if you have non-depolarizer, which are any coherent target, this PGD is 1. That means it is the purity target. So that means 0 is, of course, not possible, because as we said over here, 2 by 3. So that means we have multiplied it by 3 by 2 to make it as 1. So if you see over here, the similar kind of information, we compute the PGD, which was given by Gilles and Barnaby with us, and we are trying to see the same thing as our PGD. Similar information, but as I said over here, there is a stretch in the contrast, but you see the water body, which has only a single scattering or coherent scattering over here, corresponds to a high purity over here. Similar thing can be also observed over here. If you have it over here in the area which you have forest or vegetation cover, the PGD is somewhere in between. So it's a mixed kind of thing, and similar thing which happened over here also. And in the urban area, again, the purity has increased over here. Not as pure as you have it over the water, because here it is much more purer. Here it's urban area mixed, of course. So you have the purity on the higher side, of course, over here, but you're able to discriminate at the first instant. So we are able to, again, discriminate the purity in the scattering mechanism. So this is the purity. You can see it for the other images. This is, again, for the ALOS image. You can see similar trend, of course, in the PD and the PGD over the area which has coherent scattering mechanism and, of course, incoherent scattering mechanism. You can see it over the ALOS 2 image over Mumbai, to have over here very mixed kind of thing, because it's an urban area, but very, very dense area. but over the sea, this is the Arabian Sea. You can see over the sea, it is quite pure. It's again the same thing you can see over the mountain area. Of course, over here you have again a mixed scattering over here. At some places you have something which is coming somewhere between 0.5. It's in between the purity. Nothing is very low, but you have somewhere over as in terms of 0.5 to 0.7. That's it. So it's an area where you have something like a mixed over here. So the purity over here, same thing which characterizes by our PGD over here, but of course again with a different contrast scenario. So that means again we are able to characterize the target, a scene, in terms of the role invariant parameters, in terms of the scattering type, the alpha GD, the tau GD, the helicity parameter, because the alpha was unable to characterize targets which have similar nature or similar values. You are able to look into the purity aspect, the purity of scattering with the PGD. So here we were able to utilize three parameters, the alpha GD, the PGD, and the tau GD to again characterize the scattering mechanism from a target. Here, in this case, the fundamental idea, the fundamental philosophy over here is to utilize geodesic distance. So it's totally based on the geometry of the PolSAR data as such. Moving on to the next one, as I mentioned that here we are utilizing the framework, a unified framework, where in the first instant we are giving some role invariant parameter, alpha GD, tau GD, and PGD. We are the three role invariant parameter bounded. The next part which comes under this umbrella of the unified is the power, because as we have seen that we have decompositions where we have powers which characterize the target in terms of the surface, the dihedral, the helix, and the volume, and so on. But on the other hand, we also have in the eigenvalue, eigenbase decomposition types, we have parameters which characterize the target, which are which are role invariant, and so on. So here we have seen the three parameters which are role invariant. Can we use the same analogy, the same framework to find out powers? That's the next one, is to finding out the scattering power. But here the emphasis over here is on the factorization. I'm factoring it out over here, because as we have seen before, in conventional decomposition, model-based decomposition, what you have, you have the measured covariance, the coherency matrix, and then you are fitting in the model, the surface, the dihedral, the helix, and the volume, and so on and so forth. You're fitting in the model and trying to get the powers out, each one of them, which characterizes them. Here we are trying to find out factors. The factors will be in terms of the geodesic distance between the observed, the observation, and the canonical targets which we have at our disposal. How can we do that? Well, the idea is simple. Simple in the sense that what we have at the first instance, we have the span. Span is the total power you have with us. How can we discriminate or can break up this span into several components? I wrote over here n input models. So you can generalize into n components, because as we have seen, we have before decompositions where we have 3, 4 or more. We'll talk about that later, a little bit later. But here, can we generalize into n input scattering model? Yes, we can possibly. But how do we do that? Thing is simple. So the idea is, how am I breaking it up? I'm breaking up the span. It's equal to span into a factor over here. The factor comes from where? The factor comes from, again, the geodesic distance. Again, what I'm doing, I'm utilizing the geodesic distance, but now I'm making a similarity measure out of a distance. 1 minus the geodesic distance, the similarity measure. So similarity measure between the observed and some model over here. This is the model I am taking from literature, which is, there are so many of them, canonical target. You can take any one of them. So I'm taking this as the geodesic distance between the observed and the model. So 1 minus of that becomes similarity. But I'm multiplying with that all the other dissimilarities between the other k minus 1 model. So I have the kth model over here, the k minus 1 other, all the models are the dissimilarity measure. So I'm factoring it out over here. So the idea is that I'll have the dissimilarity. So that means the similarity measure multiplied with all the factors of the dissimilarity, and then summing them up over here. But as you can see over here, it's very obvious over there that whatever models I take and I do that, I will be always left out with a residue component. There will be always a residue component. So the residue is nothing but the other components which are there and the factors of that. So I am able to make the entire thing into something like a factor over here and a residue, which means that I am able to find out all the components which are coming over here. That means given a model, given any number of models, I can find the factors out of it. So I'm not, I am not kind of restricted to whether to use a 3 or a 4 or no, not that. I can use any number of models because of the fact that I always have a residue. That means if I'm able to fit in more number of models, my residue goes on decreasing. That's it. But I'm able to do the other factors as well. And this is, if you think over it, this is similar to something like the Hoynen approach, iterative Hoynen approach. That means I have the total power, which actually I am breaking it up into this kth model and a residue. But I'm doing it over different kinds of model, the factors are. And this is what is a new way of thinking it, where I am not calling it as a decomposition. I'm calling it as a factorization because it's not the conventional way of doing decomposition. And I would say adding or fitting in the models to the coherency matrix. But here I'm factoring them out, utilizing the similarity measures coming from the geodesic distance and the dissimilarity measure. So I can utilize them again. The nice part of it is, again, I can utilize them for both coherent and incoherent, because as you have seen, we have segregated. When I started, I segregated it something as a coherent decomposition and an incoherent decomposition. But here it again comes under the same framework. I can utilize them as again a coherent decomposition. What I do, I utilize the input models, any number of them, symmetric models, the dihedral, nanodihedral, trihedral, cylinder, dipole, name them, and you can put them inside this vector. And I have some helix components, some asymmetric components. So I can take those symmetric models and I just do something which is called as a design in terms of Hoynen, but it's something you can think about, or rotating it and then finding out the maximal similarity between those targets. That means I have an observed canoe. I take that, I rotate it, I find out the minimum geodesic distance, which means the maximum similarity, and which corresponds to that theta. I'm taking that theta and rotating everything. That means I'm trying to bring all of them in terms of the maximum dominancy scattering one. So when I have that, I select the models. I can find out the similarity measure, which is simple as that, which is nothing but the 1 minus GD. It's as simple as that. And you sort them out, because you need to sort them from the dominancy, the highest dominancy to the lowest dominancy. I just sort them out in terms of the dominancy. As soon as I sort them out, I can form the convex weights out of them, because it is nothing but the weights. And this is then utilized to find out the similarity and over here the residue component. So this is just the weights which are utilized over here. And this is again, which is the residue component. And simple as it, the next part is you multiplied with the first element of the canoe matrix, the observed canoe matrix. 2 times of K11 is a span. We all know that this is the span. So the span multiplied with this element over here gives me the powers for each one of them. And the last one remains the residue. That means whatever the models you have, you get that many number of powers corresponding to that convex weights. So you see that this is a coherent factorization over here. It's because I am utilizing all the coherent models, the scattering models which are there in literature. I'm taking them up and forming this as a simple one. And as I mentioned, that coherent decomposition, well, there are some limitations because, as we know, because of the coherent nature, you have speckle, which can be a problem to, and also this coherent of course decomposition, and in this case factorization will be helpful for targets or for scene which are high resolution and low entropy, or target, or in the scene you have a single target to characterize, something like that. So in that cases, coherent decomposition plays a major role. So if I just look into an image which as an SLC image, just cropped it out from an analogous to image which contains ships over here, and if I start utilizing my information which coming from my coherent factorization, I'm able to actually characterize them in terms of the scattering which I've taken. I've taken the dihedral, the narrow dihedral, the trihedral, and so on and so forth. And I can break it up into the dominant. I can break it up into first dominant, I can break it up into the second dominant, and I can go on and on. Because this is what I can do with my geodesic distance, because I have already formed the similarity and I can sort it out. And you can clearly see, it's very nice to observe that if you see that the water, of course, which is very obvious, will be a trihedral measure. It is something like a one which has a single scattering mechanism. And if you see those ships, they are a mixture of kind of a dihedral and narrow dihedral. You just see very closely, they are a mixture, which is true over here. As soon as I come to the second dominant over here, the water body changed from being trihedral to a cylinder, which again is very true. So, and this, if you start seeing the ships, it is now a mixture of narrow dihedral and some helix parts. Some of them are a bit of pink over here. So if you are trying to see on and on and on, of course, beyond even third and beyond, then will be too noisy to analyze anything. But to understand the dominance in the mechanism, you can clearly use this information which comes from the factorization framework. And then it's simple, you can just utilize them to find out the power component. So that's what is very, very effective and important in doing this kind of a framework with the factorization framework. And as I can say, I have done for coherent scattering. I can also move to an incoherent scattering mechanism. But in this case, what do? I have the similar thing where, well, you don't see anything different as such over here. But what you have over here, I just incorporate a volume model over here. In the previous case, it was we had only the canonical targets. But here I introduce, along with those targets, I introduced a volume scattering component. And in order to utilize them, I utilize the alpha GD over here. The alpha GD, which we computed over here, which finds the scattering mechanism, the scattering type. I utilize them to find out a branching condition that if alpha is within that bound, I go to one branching, or otherwise I go to another branch. That's the only difference. And the branching over here is just as simple. In one case, I compute the volume together with the other components. In the other one, I separate it out, the volume component from the other, because depending upon this alpha. So this is how I do the same mechanism. If you see, there is no difference at all. It's just that I would have the input models over here. I do the same design with respect to theta to find out the maximal similarity, this MS over here. Here, only the difference over here, as I mentioned, is the branching condition depending upon the alpha GD greater than 30, greater than 40. This comes from studies which has been seen with different kinds of volume scattering model in the literature, which has been used for model-based decomposition. We have tried to see them and see alpha GD probably lies between these to make the branching condition. So this is the branching condition for utilizing the alpha GD. And then we meant for the two cases, we find out the similarity, we find out the same as dominance, and we find out the convex weights again over here. One over here, we find out separately the volume and the other scatterer. Here we combine them together. That's the only difference. And then we multiply them with the first element of the Canoo matrix, 2k11, to get the powers. So as you can see, no difference as such from the current, only that here I have introduced the volume model, because this vector, I can take any models I can take. So I have taken all other of them to be as canonical target. One of them, of course, over here is the random volume model. You can take any other volume model you want. It's up to you, because this will not change at all. And if I do that, I did it for the San Francisco area for a radar set 2 image. And you can see again the dominance map, which is again very nice to see. The water body over here is again a trihedral, which we have already seen before. But the urban areas over here are narrow dihedral. So it's not dihedral because there is some kind of a mixture. So the dominant over here is a narrow dihedral. The first dominant are narrow dihedral, because dihedral, you have to be pure in that case. What happens in the second dominant, you have the dihedral. So, and the from third onwards is goes on to be much more difficult to characterize, because it becomes noisier, because you don't have proper anything. But at least for the first two, you can get information about the dominance in the scattering mechanism, and it's able to characterize different targets as such over here. The thing over here, you see this bridge over here, and the first dominant, it is dihedral. For the urban area, the first dominant is narrow dihedral. The same over here, the second dominant over here is dihedral, and it is a kind of a mixture of narrow dihedral and mostly narrow dihedral, but a mixture of narrow dihedral and dihedral. So this gives you a very nice way of characterizing the target, just not going to the power. Power comes later on, because you can always turn this into a power. So the thing is, you are able to characterize the dominancy mechanism. So you are able to have the physics of scattering more, you can able to find out more information. So that's what is it. Information extraction is much better in this case. So again, as I said, you can, over this image, you can find out again the dominant scattering mechanism. As you can see, this is, I just made it into even, odd, helix, and volume. I just made them into, I have shortened them out, so that I just want to show what exactly it is. So even comes over here in terms of both narrow dihedral and dihedral combined and so on. And you're able to see that it correctly characterizes it. And I just convert them into power, just multiply them, each component of them, with the Canoo matrix element, the 2k11, and you have the power. So similar as you would have in a model-based decomposition. So here I again showed the PD, PS, and the PV, just to have a false color composite, and it characterizes very well the area. The urban areas are very, very nicely coming out. Here you have the C. Here is a combination of more of surface and a volume, a bit more mixed over here. You have this area over Mumbai. It's very nice captured. The urban areas properly captured over here. This is the area where you have a thick, very thick natural forest over here. It's also nicely captured in the volume component. These odd bounds is seen very well in the ocean over here. The even bounds are seen, of course, in the urban areas, and over here also in many ships over here, which is a port over here. It's very, very nicely seen. Helix, of course, is the occurrence is so minute, you're not unable to see them. They are there, but very, very few. If I just want to turn them into power, I just multiply them with the 2k11 factor to get the span multiplied by the convex weights, and I'm getting the power out of it. This image is again from the ALOS 2 RGB from San Francisco. Again, over here, we are able to get information from the urban area, and we are able to characterize it very well, similar to the one before. Again, if you want to find out the information from the power component, we just multiply them with the 2k11 component, and we are able to characterize them, the power component, in the false color composite at RGB. The next one, of course, is the area where you have the mountain area of snow. This is a bit complex, of course, over here, but still we are able to get fair amount of information about the type of scattering which possibly could be there. Somewhere over here where you have some dry snow area where you have kind of a volumetric scattering, some of the areas which are due to the plane, or some of them could be possibly due to some effect of the topography. You can see some of them to be as odd, but you have to take care about the topography. Is very high over high altitude over here, but some of the topographic effect also comes into picture over here. The area which is forest area also is nicely shown over here, because as I said, this is a forest which is not so dense but also frozen in some sense. So you are able to characterize again over this area, which is again complex due to the complex scattering from the snow and also the topography. You're also able to get the information from the scattering powers also similarly. So in nutshell, we have seen that this unified scattering type in philosophy, the framework, we are able to characterize first the scattering components, which are in terms of the alpha GD, the type, in terms of the purity, in terms of the purity in the scattering, in terms of the PGD, in terms of the helicity, the asymmetry in the scattering, in terms of the tau. So we have characterized them in terms of the three role invariant parameters, compare them with the existing ones, and we're able to show they are similar and are able to characterize better because of the enhancement, of course, due to the way we are utilizing the geodesic distance between the Kano matrices. We are able to again translate it also in terms of the powers. We are also able to utilize the information in terms of the information in terms of the similarity measures, which are again utilized in terms of a factorization framework, not of the composition. A factorization framework, which we are able to then characterize in terms of the power components and n components of them. So n component plus a residue. So we are able to generalize it to any component which we can have in literature. It can come from a single target, it can come from a compound measurement target, but as long as there exists a scattering matrix, we are able to convert the scattering matrix into a Kano representation, a 4x4 real, and we are able to utilize our framework. So it is general. It's a general framework for n targets and a residue, and you are able to see also that we can also generate an intermediate products, which are the dominancy products, which are useful in order to understand if you have some complex scattering mechanisms, or you want to characterize two extremely different kinds of scattering mechanism. You are able to characterize them utilizing this concept of dominancy, the first dominant, the second dominant, and so on and so forth. So then you can utilize them in order to find out the power component also, which is nothing but the power, the convex weights of each one of the target multiplied with the first element of the Kano matrix, the 2 times first element, which is this band. So with this, I come to the break. So I think we can take a short break in between, and we return in 10 minutes. I give it over to Andrea.
Yes, Avik, thank you very much. I have to say that there are a couple of questions in the Q&A box that have come along through your very interesting talk. And the first one is, when does the principle of reciprocity not hold? Is it guaranteed as a fundamental consequence of Maxwell equations, or is it just so common for targets that it's always assumed? This is, I think, this was about the first part of your contribution when you were discussing main characteristics. So if you
thank
can.
you. Thank you very much for the question. It comes from, I can see Thomas. Thomas, good question. As far as I can understand, that this reciprocity theorem would not hold for bistatic scattering, where HV would not be equal to VH. But yes, it's a fundamental, of course, consequence when we take into account that you have a monostatic where you can, when you change the antenna, and you say that when I change the antenna so that HV is equal to VH, and this is applicable for a monostatic case. For bistatic case, it won't happen. But if you also understand it in this way, the principle, I mean, from the principle of Maxwell's equation or the principle of fundamental is that if the electromagnetic wave which is propagating and which is interacting with the target as such, if it is not changing the property, the intrinsic property of the target itself, then in that case, HV will be equal to VH for a monostatic case, which of course we assume that it will not change the intrinsic property of a target. And in that case, HV will be equal to VH. But for a bistatic case, because of the geometry, HV is not equal to VH. Thank you, Andre. So, okay, so we have found the powers, and that's what. So we go to the next one, which is the part 2, which is target characterization using a model-free approaches. Now, what does that mean over here? We'll just try to again analyze it briefly over here. So the idea is that, as I said again, so we are incoherent decomposition principles comprises of, again, as we have seen, model-based, the eigenvalue, eigenvector-based, and the new one, which is this power factorization based, the unified approach. And the last one I'll be talking about is a model-free approach. Now, why this is important and what it is bringing in as such. Now, there are different dichotomies, right? I say in the PolSAR data analysis. Now, what are they? As by now you have already seen, or you know it by yourself, by your study of PolSAR, and through this also, is that you are able to fit into different models coming from surface, dihedral, volume, helix, and of course there are many more. If you see the literature, you are fitting them in the coherency matrix. The observed coherency matrix over here is T, and with some factors which corresponds to those scattering, I'm trying to fit it. Now the idea or the question is, how far can we go, or can we just go on and on doing this? Is it possible? And what happens in this kind of situation? So the idea is that what are the things which we are looking at when we are doing such kind of thing? We are looking at the information utilization. What do I mean by this? Information utilization means how much information which is there in the T matrix I am able to consider when I am trying to fit into this model, which means that there are this contains the real part and the complex part. So it contains the T11, T22, T33, the 3 diagonal elements, and you have the T12, T13, and the T23, which contains the real and imaginary part. So the idea is that, am I able to utilize all the information which are there contained in this T matrix? Maybe yes, maybe no, I don't know. So if I just see the first of them, the Freeman-Durd and the Yamaguchi and so on and so on, they only utilize partial information from them. They only utilize only few elements which are occurring over there. That means that's what I called as the information utilization. Am I utilizing all the information? So this is one thing we need to understand. The next thing is that, as we have all know, or they've all seen, is that in doing so, what we have in a decomposition, model-based decomposition, we have negative powers, values which are negative, and this is quite common in model-based decomposition. Negative powers doesn't make any sense, but how can we remove that? Because this is physically not a possible thing. So we need to look into this aspect. Model inversion priority. That means which of them am I computing first, and which one of them I'm computing second and third, and so on and so forth. I mean, am I computing them, all of them simultaneously? No. I am first computing something, then something, then so there is a hierarchy, a branching. And this branching depends upon certain criteria. So there's a criteria, and then depending upon those criteria, we have branching. So that's what I called as, sorry, model inversion priority. I'm giving priority to which model over here first? Am I finding out surface first and then helix and then dihedral or something like that? No, usually not. Of course, it's not no is not none, but usually not. There is a way of finding out, and that's how it is done in 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 the literature or in. And the next one, of course, very important, is computation efficiency. In doing so, in doing this model inversion and also utilizing the information of all the information in the coherency matrix, how much am I able to utilizing computing efficiency? I mean, it is too complex to actually understand what's going on, or it's simple and so on. I mean, this is the computational efficiency, both in terms of understanding and of course both in terms of the machine also. So these are some of the things, 4 things. There can be many more, of course, but these are the 4 different things I try to question upon. They are there. So what people have done, I mean, this is there for a long time, since the starting of the decomposition principle as such. We started with Freeman and Durden in 1997. So it has been there, and people are trying to give very different models, starting from Yamaguchi, from 2005, and again the modification of that 2011 and so on. So there are different decompositions which have been given by many researchers throughout these years, with lot of sophistication in trying to make more number of components, not only 4 but more number of components. They can come from different, they are characterizing different mechanism, they are characterizing different compound mechanism. They are changing the volume scattering altogether to make a different volume. The volume can be adaptive and so on. They can have criteria for removing this negative power. So there's a criteria which then nullifies this occurrence of the negative power, and then you do again the decomposition in a different way. So model inversion, of course, the priority again more or less remains the same, but again the branching conditions become more and more involved. I would say the branching conditions are more and more involved. So you have to really keep a track of it, because it grows and grows and on again, because the model increases and the complexity increases, and the inversion priority also increases. So you have lots more criteria to fulfill in order to get to a branch or not, and so on. And with that, the computation efficiency also increases. A newer approach also is that people have also tried to incorporate PolSAR with PolSAR data. This is a newer approach. I will not go to the detail of that, but there are literature papers, you can look into them, where they have reduced the computational efficiency. They are doing in a very nice way, but there are other things which need to be taken care of. So these are all different decompositions which have been there through years. Well, I have not maybe made the very recent one, but well, it is still recent, 2017. And people have also introduced different kinds of rotation matrices to take into account different conditions, to remove these negative powers and so on, and take into account the phase information in a much better way. There are decompositions which have also introduced stochastic distance measured in method, in which they are able to compute the stochastic distance and then improving the powers over other decomposition in a very nice way. So it's one of its kind. There are decompositions where the degree of polarization has been brought into picture, where it is used as a criteria again, of course, a criteria, but it has been introduced into the decomposition concept. So as you can see, there are different ways in things which have moved, and it's going ahead a lot in this direction. So in all of them, you have to look into that information utilization, whether I'm able to utilize all the elements of the T matrix. Am I able to just remove the negative power, make it null? Maybe not in some cases. The priority in inversion, the branching condition, how many branches do we have, and Can we just reduce those branches, or can we just get them just over? Can we just don't need a inversion priority at all? Can we have them simultaneously? All of them compute at one go. There is no way of branching, and reduce, of course, the computation efficiency. So this is where we stand today, the idea. So the idea was that just kind of going away from this way of thinking in terms of the decomposition as it is taught in the conventional way. Can we have a little bit more in an unconventional way kind of thing? And that's what I call as a unique way out. What is it? What I do is over here, I try to take the elements of the coherency matrix, because that is what is there as a measurement. I take into account a parameter which is called the Barakat degree of polarization, which was given by Barakat in 1997, and has been not used so much in SAR polarimetry. It actually comes from optical polarimetry, ellipsometry. It has been used a lot in polarization of light as such. So can I use this information over here? It's a degree of polarization, of course, but an unconventional one. It is not the same. It doesn't give the same information as you think the degree of polarization from the work of Born and Wolf. It's in a different form, because it doesn't characterizes all the invariants. It is only one invariant among them. I'll not go to the detail of that. You can find it in the paper, of course. But just to give an idea that yes, it is a measure of degree of polarization, but only one variant of it, only one variant of the degree of polarization of scattering. It's introduced within the decomposition framework. This is very new. It characterizes in a similar way the amount of purity, as we have seen. It characterizes whether a target is polarized or unpolarized. But as I said again, that it only conveys one invariant of that. And the idea is that can I incorporate these two, and I form a scattering type parameter. The scattering type parameter, as I mentioned again earlier, is something like the parameter of cloud, let's say. I mean, the scattering type parameter, which characterizes the scattering in a continuous scale bounded. Similar, also maybe somewhat similar also to the alpha GD. But I am just utilizing these two parameters over here. Simple, you will see that it is the elements of the coherency matrix, and only this parameter, the Barakat degree of polarization. I am trying to find out the scattering type parameter. And utilizing scattering type parameter, I'm immediately getting the scattering powers. Just simple as that. What my idea is? The idea is that it's model free. As you can see, nowhere I have talked about any model. And in that sense, I am justifying uniqueness. That means I have the measurement, which is in terms of the coherency matrix. And this is a measurement from a target given, and it's unique for a given polarization and for a given scene. So this is model free. The scattering type, this parameter over here, and the powers are computed simultaneously. At one go, you get the scattering powers, the type and the powers. So as I mentioned over there in the previous slide, that you have this criteria where you have to look into that. If this is this, I go to a branch and so on. So there is no branching over here, no hierarchy, no criteria in the computation of anything over here. It's direct. So I want to remove this hierarchy over here. There will be no non-negative power. I'll show you how. And the best part over here is I can simply move from full pole to compact to dual copole and possibly bistatic in a similar equivalent way. I don't have to change any formulation, because what happens is now when we do decomposition, when we say polarimetric SAR decomposition, we are utilizing a full polarimetric SAR image, and then we are utilizing the way as I have shown in my earlier my slides. You are able to fit the models over here. Now, tomorrow you go to a compact polarimetric SAR data, and you have a totally different way of doing decomposition. As I'm not mention it over here, but you have to go for the M chi, the M delta, and so on. There are so many of them, literature are there, and you have to go to a different ways of doing things altogether. So the idea is that I have to change between when I'm doing for quad pole, when I'm doing for compact. Dual core means something like the TerraSAR-X HHVV kind of a mode I'm talking about over here, not the HHHV, but it's not the dual cross, but the dual core I'm talking about, the HHVV kind of a mode. There exists one decomposition, which also is a model-based decomposition, as far as I know, the dual copole based, and it is a two-component decomposition, which is pretty new, of course. And bistatic, well, I've not seen any as such. Well, there are some of the analysis, but I'm not talking about that in this part. So the idea is that there is an equivalency when I'm trying to extract this information and from all the different acquisition modes, which is very, very nice because I don't have to change anything at all. And the next is I'm able to have the role invariant nature of the scattering type. Why? Because since, as I mentioned over here, that I will be utilizing the scattering type parameter, and this scattering type parameter by its very construction is role invariant. Since this is role invariant, my powers which I will be computing out of them are also role invariant. So that's also very nice. Otherwise, we have to rely on a basis. Is it an HV basis? If I go into some other basis, I have to just do the transformation. Well, it's not difficult, but there is an extra process in which we have to change the basis and work on that basis itself. But here, you don't have to do that. They are role invariant. So you can just do the same thing. It will not change. The powers are all role invariant. So this is what I call as a unique way out. So let's go to the methodology and try to see how do I do that. So I try to take these two things. I just defined a quantity, the T11, the coherency matrix first element, and I divide it. I take the ratio of it with the Barakat degree of polarization M multiplied with the span, and then similarly the T22 plus T33 divided by this span multiplied by this one. Now why so? If I see that, I have the T11 as the first element, T22 as the second element, T33 as the third element. Very simple. The span is a summation of all the diagonal elements. This is all known. Simple as that. Nothing great over here. And the Barakat degree of polarization is defined in this way. This is the formulation of the Barakat degree of polarization. I'll not go into the formulation over here because that's totally a different talk altogether. But believe me, this is this simple, very simple expression of the Barakat degree of polarization in 3D. 3D means this T is a 3x3 matrix. So this is in 3D, it's in this formulation. If you change this 3x3 matrix into a 2x2, which is a covariance nature, where you can have it for a dual copole, it simply reduces to 4 times of this divided by trace square. I mean, I just know it, I'm telling you, but you can simply do that. So this is the expression of the Barakat degree of polarization, and it varies between 0 and 1. So it's completely polarized if it is 1, totally unpolarized, it's 0. But as I mentioned, this characterizes one of the variant, and that's enough for characterizing targets for our Earth observation cases. So what I'm doing, I'm trying to find out 2 parameters, which are just the ratio of the first element and the combination of the two second elements of the diagonal elements and the Barakat degree of polarization. So this is so you can think about this. This is a polarized part of the total power. This is nothing but T1 divided by the polarized part of the total power. This means over here. What I do, I just simply take the difference between them. So tan theta FP is nothing but just this difference, tan theta 1 minus theta 2. So doing so, I come to this, what I call as the target scattering type parameter theta FP, which looks like this. So what you have? You just have the elements of the coherency matrix, just the diagonal elements of the coherency matrix, combination of them. You have the total power span, which is nothing but the summation of all the elements. And you have this MFP, which is the Baraka degree of polarization. And this you can see easily, this varies from minus 45 to 45. Now, how does it make sense? And if so, how? If you see, the T11 comes from the scattering from a regular part of the target given as A0 by Hoyne. So this is from the Hoyne point of view, this is nothing but the A0 element from the Kano matrix representation or the T3 matrix representation. The second one comes from the irregular part of the scattering, which is nothing but the T22 plus T33. If you just sum them over, you get B0, which is not the irregular part of the scattering mechanism. That means these two make sense over here. And this quantity together, T11 minus T22 minus T33 is again Rolle invariant. This is a beautiful thing. And each one of them gives information about a regular part and an irregular part over here. And both of them actually come from Hoyne phenomenological theory from his PhD, which is a wonderful work starting off radar polarimetry from 1970. So I'm just going back to what and trying to relate them. So if I relate them, this relates very nice way. And if I see them, they are so easy to compute. Span is just some of them. This is nothing but just a simple MFP, as you have seen, it's only a determinant and a trace operator. Nothing at all. So just utilizing that, I'm able to compute a scattering type parameter, which varies from minus 45 to 45. Minus 45 characterizes scattering from a dihedral, a pure dihedral, and plus 45 characterizes scattering from a pure trihedral. So similar to as what we have in alpha, or you have seen in alpha GD and so on, this also characterizes a similar way, but just a different scaling altogether. That's it, but a different scale, but bounded. 45 minus 45 comes from a pure dihedral, pure trihedral on the two extremes. And I have this scattering all continuous and bounded over here. I'm able to characterize it. And this is, as I mentioned, this is the Baraka degree of polarization, the MFP, which varies from 0 to 1. So I'm just utilizing again the very fundamental given long back by Hoyne in his beautiful thesis. I'm utilizing the concept coming from optical polarimetry, ellipsometry, which is utilizing the Baraka degree of polarization. Well, they mention many other types of parameter, but this is one of them, very important. I'm just utilizing them in tandem for my radar measurement. And I'm able to get this new parameter as the scattering type information. And utilizing this information, the scattering type parameter theta FP, I can simply, very fast, get a 3-component decomposition. All the powers are Rolle invariant, as we mentioned. So what I do, I have the MFP, and what I do, I can find out a diffused kind of scattering. So this is, you can say, in analogy or equivalent to something what you have as a volume scattering. But what you have, volume scattering means there is a model. There is a model associated with the volume. Here, there is no model. So what I have 1 minus FP, which characterizes my amount of depolarization in the wave structure. Multiplied by the span gives me a diffuse power. Straightforward, simple. This characterizes the diffused power. So I compute the diffused power first, and then I compute the residue power. The residue is simple, nothing but the span minus the MPV. It is nothing but the polarized part only. It can be very simple. This is the diffused part, and the remaining part, residue part, is nothing but the polarized part is coming, and I give this polarized part into the other two components, which is nothing but my even bounds and my odd bounds. How? By just having PR, the residue, by 2 and multiplied with a geometrical factor which comes from my scattering type theta FP, because it's a geometrical factor which takes one to the one end and the other to the other end, if you can just see very well. So if I have theta FP to be minus 45, this will be only PD, PS is 0. If I have theta to be plus 45, this is 0, this is totally PS. And depending upon M, how much the M is, this will modulate the amount of how much is the diffused and so on. So this is a very elegant way of doing it and very fast. So I'm able to compute the scattering type utilizing the information coming from the very fundamental of Poinan, utilizing only the elements of the coherency matrix, and I'm utilizing all of them because I'm utilizing the diagonal element and I'm utilizing the MFP, which contains the determinant and the trace. The determinant contains all the elements over here. So practically I'm able to utilize all elements as such. And I'm able to get also not only the scattering type information, but also the powers at the same go. The PV, diffused, even bounds, and odd bounds. So that's what I called as the three-component model-free decomposition. So because if you see, the most widely used till today is the Freeman decomposition. Of course, there has been sophistication done, but if you want to do something very simple and fast and no, you can also, of course, apply the Freeman decomposition. And here also, you can also look into the three-component decomposition. And here, as you can see, that it also has other nice properties. They are role invariant. You do not have to look into the role because that is not there for the other model-based decomposition, as I mentioned. These are all non-negative powers. There is no way you can have a negative power because this is between 0 and 1. This is the diffused power. This is positive. These are all positive powers. There is no way you can have non-negative. All the powers are positive guaranteed. So by doing so, you have the three component, you have all the other properties. You don't have any criteria, no hierarchical criteria, no branching condition and so on. And the computation efficiency is very, very fast. As you can see, they do nothing at all. If I just try to look into how they look like, and if you see this is the image, you see this, I just scaled it because the alpha, as you have seen, the alpha, this underscore is between 0 to 90, as you have seen for the cloud. Alpha, I just scaled them so that I can have the same scaling to compare. I just made 45 minus alpha, nothing very great. And I see that they are corresponding. So they are able to characterize similar way. Maybe in this case, you are again able to get a bit more contrast. So here you are able to okay, sorry, stuck. So here I am able to also get the powers. So I'm just comparing with the Y4R. I think this is a very, very nice decomposition, which takes into account the rotation and then finding out the four components. And this you can see that you are able to get the three components over here. The helix, of course, I'm not put, so it is the three component false color composite. And utilizing the method over here, you are able to see, you are able to get quite nice the powers over here. The urban areas are very well captured. The other areas are also very nice in terms of the contrast and the information content. This is just the three component which we have used, the diffused, the surface, and the even. If you just try to see over a particular area, what I've taken, this is for the radar set 2 C-band, I have taken it over some oriented urban areas. So just take a clip, a zoomed part over here. This is oriented to the radar line of sight, severely oriented, almost 45 degree. This is an orthogonal urban area, but of course there's a mixture over here, these urban areas. This is vegetation area, but as you can see, it's sparse over here, not so much dense, and this is the ocean area. If I try to see over the rotated urban area, I see for the Freeman component decomposition, I see, well, it's only volume, because as I have mentioned that because of the orientation, you have lots of power which comes from the cross-polarized power. So the cross-polarized power is entirely given to the volume scattering power. And that's misleading. And this is severely misleading. You are able to see a rotated urban area, but you see volume. And if you start analyzing them, doing some clustering, classification, and so on and so forth, well, you will be in trouble. On the other hand, if we see with our, we are able to get the dominancy, of course, with the urban area, which is the dihedral scattering, PD. But of course, as I mentioned, there will be some other scattering also over there, because this is not, of course, totally pure dihedral. There will be mixture also over here. In the urban area, of course, you see, well, now you are starting to get dihedral, of course, over here, but still it's less than the proposed, and of course, there'll be other. So it's similar, of course, over here in the case when you have urban area, orthogonal urban area, but there's mixture. But also in our case, the dominance is much better than the one. In vegetation, of course, you get only this, but as you can see, there's a mixture of many things. So it's not only you get PV power, because over here, as I mentioned, you are fitting a volume model, which comes from the random mixture of of dipoles, randomly oriented dipole. So here you are giving a kind of a particular type of a model to this, which may not be able to capture effectively. Here, there is no model. Everything coming from the depolarized part of the wave. And you are able to get some other two components also. The ocean area is, of course, much better characterized with ours. So in all, we are able to give a much better information in this. I'm coming to my own image of Mumbai, this area, again, the same area, urban area over here. You're able to capture a little bit also with the alpha, cloud alpha. But with our also, we are able to capture in a nice way the amount of information with the theta FP. If you go to the powers, it also characterizes similar to many areas, but in some areas may be also better in the sense. So you are able to characterize nicely the image with different kinds of power components. If I again go to the same area, exactly the same area I have taken, and I utilize the ALOS band over here, the ALOS L band image, then you see over here what happens. The same urban area with ALOS, you still have the same problem. You have the F3D, you have the PV, but slightly but negligible amount of power coming up. The proposed one is able to again characterize as better in this case, but here also you have surface scattering more because of the penetration capability possibly of the L band, where you are also able to get some surface information also. So that's possibly the reason, because of the longer wavelength. The urban area over here again looks similar, but again the dominance is better. Similarly, also the same thing for vegetation. You are having not only the volume, but other two components coming up. This could be the dihedral, which is coming from vegetation, dihedral, that from the tree trunk and so on, the ground. And so this is the dihedral within the vegetation, possibly, kind of thing. And it is also nicely marked over here. And of course, the surface ocean area characterizes again better off with the PS component, the PS power over here at the surface. So again, all in all, we are able to characterize nicely with the proposed one, which is, as I mentioned, model free, non-role invariant, because which is clearly from here that I am not dependent upon this angle, which is the role invariance property over here. If I have to make this Freeman-Durden decomposition better, then possibly I have to rotate the T matrix and then apply the Freeman-Durden. So it is rotation compensated Freeman-Durden. Possibly would be giving me similar result. Well, I've not tried that, but this is what I would say from here, from the understanding. But here I have to do nothing about that because my theta is role invariant, and I'm just using the span over there. So everything over here is role invariant. I don't have to bother about that. So also I'm able to characterize it with the scattering type parameter, the theta FP, but at the same time also characterize it with the power component also. So this is the new approach for utilizing model free, which brings into the concept of regular and irregular target coming from Hoynen. Also utilizes the information from the degree of polarization, of course, the non-conventional one, the degree of polarization introduced by Barakat, and bringing them together, and we are able to get nice information about the scattering type. So from here, let's go to the last part of it with the application with novel descriptors. Whatever I have talked about in my earlier presentation in part 1, I'll be utilizing those parameters which I've extracted from them, and I will talk about a few of the applications which we have done with our collaborations with different researchers, people from all around, from different kinds of applications. I'll just look into 4 of them because I think that will be only time will be there to cover these 4 aspects. But of course, there are a few more, and few, of course, a large amount of results are also there inside in this also. But I will not go into those details. If you are interested, you can look into the publication. So going to the first one is just to characterize snow cover changes. So land cover change analysis, but only in terms of snow. We have done quite some studies with the snow cover from in the areas which is the foothills of the Himalayas, in the snow-covered areas in multi-temporal analysis of the radar set 2 coverage of the same area in February, March, and in August, where you have the snow has already melted. It's summer in India, but in these 2 months you have the snow cover at its peak mostly. So the poly-RGB of them looks something like this. The RGB poly-RGB composite of February and August looks like this. I utilize the geodesic distance again measure just to see between the first and information between how they look like between these 2 images between February and August. As I said, here you have the snow covered, here mostly it is snow melted. So I'm able to get some information about the difference. So this is just the geodesic distance between them. And if I just do a simple thresholding, nothing very great about it, just simple thresholding gives me a snow cover map, which at the first go looks quite impressive. This is for the full pole. I utilize a full pole information over here, but I can also utilize the HHVV information, just the dual pole, and formulate the K, the canoe matrix for that, and I do the same thing with the same image. The idea is that if I do not have full pole, if I have only the 2 co-pole information, what do I do? What do I get? I get the same information. I do the same thing again over here without changing anything at all. I get the snow cover map, which is not bad, of course, but not as good also as the full pole information. So I'm able to get a good result, but well, not as such as good as that. If I do it with, again, the HHHV component, so the co and the cross pole component, it's deteriorating. It's not as good as the full pole, of course, and not as good as the dual pole information. If I do it again with the VVVH, similar. There is no such difference as such. So that means if I just try to understand it with the full pole, I do it with the dual co HHVV, I do it with the HHHV and the VVVH, I get the maps utilizing only the geodesic distance, as we have mentioned, we have done before, between the 2 acquisitions, where you have snowfall, where you have snow, and where we know there is no snowfall, the snow has melted. And we have just compared them with the ground truth, which was done utilizing an optical image. Because optical image, I would say, gives the best. We do that utilizing the NDSI product, provided you can get a cloud free, and we were able to get only an image which was cloud free during those acquisition dates closely, not the synchronous, but we are able to get that information, and we have compared that with the NDSI product and some of our ground expeditions, which were people who were there in the field work. So utilizing that, we are able to talk about qualitatively about the snow cover. Nothing quantitative measurement was done utilizing some other techniques, machine learning techniques, but not in this part of the talk will be there. But we were able to get a qualitative measurement by seeing those information which came from NDSI products and also some of the areas where we have done some ground truthing. The idea is that we are able to utilize this information of a geodesic distance only, but utilizing just the difference between the 2 acquisitions. But the idea was that to look into a little bit more into the individual scattering mechanism, because that was the global one where we can see the change between the global one, between two scenes, and then coming up with a threshold. That's fine. That gives you a product. But if I want to a little bit look into the physics of what has happened in between, can I look into the mechanism, the observed and particular type of target? Let's look into the February data, which where it was snow covered with, and the trihedral similarity, the trihedral scattering mechanism. What I see over here, that over there where I have this forested area, where I mentioned again in my previous slide, this was a forested area, not so dense, but also frozen kind of thing. Here it gives rise to a trihedral kind of scattering. The trihedral scattering is much more over here. This is the similarity measure. Okay, just to give you an idea, this is a measure of similarity. So we have converted the distance into a similarity measure, 1 minus GT, so that we know that higher it is, that's more similar to that case. What happens to the March case? It is, so we have February, the March, it is similar, but as you can see, this has increased. The similarity has increased because you have over here coming close a little bit more of the trihedral scattering over here, unlike the one in February. But what is interesting to see, of course, over here, as we see in August, except for the few higher peaks, all of them, all the snow has melted over this region. So you get more close to a trihedral, which is very true and apparent, because here it was snow covered, here it is melted in August. So we are able to justify the physics behind the scattering and understand what's going on. Anything else can we do that? The other one is to little bit go a bit more ambitious, going a little bit more of the helix scattering, which is the scattering due to asymmetry. Now, as we have seen before, that no, we can see the asymmetric scattering is higher on the areas where you have the snow, which are there, the dry snow area, which is coming from the volumetric. That means over there is a mixture of volume and also, as I mentioned, there topography. So it's a mixture of volume plus some topography. So it's a bit complicated to understand, but what is important to see that we are able to get a discrimination over the area which you have a forest area, frozen forest area, and the other areas which are you have snow covered but a topographic effect. You have a bit of helix scattering, so an asymmetry. You in the February data, similar, almost similar, a bit more in the March data. But what is very interesting to see in the area which is in August, the helix has just gone all to very close to zero. But if you see over here, because of this complex scattering now coming from the forest, which is now thawed because of the temperature increases, you are starting to get a little bit more of helix over here, unlike which was there over here low. Well, this is nice to understand, and maybe can go a little bit more further into characterizing this, what exactly is happening with the individual scattering mechanism, not only the snow, just the snow covered now. This is a study which we have done with this thing. Urban change analysis. We have seen something where let us try to analyze it with some trihedral. So we have seen that we have a trihedral scattering, which characterizes this, and the corresponding Kenyu matrix looks like this, the trihedral something like this, and characterized by this Kenyu matrix. And I have taken a dihedral and I rotated it with 45 degree about the radar line of sight. What happens is that I have no copole. I mean, don't have this component over here. The copole goes away. The cross pole comes into picture. That means I am rotating a dihedral. As soon as I rotate at the 45 degree, I get only cross pole. The copole goes away, and I have these three Kenyu matrix to look into. I just do simple, just to see a change between the two timestamps, between each one of them, taking them to be the absolute change between them, between the T1 and T2 for the trihedral, the T1 and the T2 between the dihedral and the 45 degree dihedral, and just give a index, a change index, a difference index as the max of them. Simple as that. Just give a max over there. So if you just do equalize them, I just utilize them to UV SAR data. And this is the Google Earth image of there. This is the ground truth. And if I just try to see again what happens if I just take between the 2009 and 2015 data sets, these two, with a full pole image, I try to get the information about the changes. And the changes are very, very apparent, are much more when I look into the change which actually happened over here. There were no construction, it has been constructed over here. But you can see they are very irregular actually in terms of the structure and the shape. So that means here, somewhere you see it is reddish, some most of the places you can see is green because this is the poly RGB. So you have the areas which are oriented to the radar line of sight, you get more of HV. It doesn't mean it is an area which has vegetation, but it's an urban area. But because of this geometry, you have these things. But if I go to the HHVV component, I see similar, but a little bit kind of deteriorated than this one, than the full pole, but well, still not bad. And if I just do what is a clustering, just a technique, which is a thresholding technique taken from literature, and we just see they're able to get some information about the areas where we have the changes and we have the ground truth over here. If we just try to again see between the targets, as I mentioned, between the dihedral, the change between the measurements which is made in 2009 and a dihedral for a full pole, I see that wherever there were dihedrals were there, the values are high. Wherever there were no construction, it was very low, which is obvious. And dihedral being a prototype of urban area is what we have taken. I see the next one, which is for the dihedral for image, which is 2015. You see the changes. You see the changes happen over here. That means I am able to capture it only with my distance or the similarity measure between them. So utilizing the distance, the similarity measure, which is coming from the geodesic distance, I'm able to capture the information which is coming from a particular target, which characterizes urban area, in this case, dihedral. I go on to do certain analysis for taking different targets over here. If I just use the HH, the HV, the VV, this is just with intensity images in each one of them, the total span, and I utilize the GD, and I'm able to get better the information or this change detection which is happening over these two images. The values also tells me the same story. Next, I go to a clustering mechanism, again utilizing the geodesic distance, which is also between 0 and 1. I utilize again the trihedral, the dihedral, but here I take a random volume. I take this similar one as it is taken the random volume for the case of Freeman-Durden decomposition. So I take these three elements over here, trihedral, dihedral, random volume, and I again try to find out similarity between them, the observed and these three of them. I form what is called as the normalized component. So this is normalized with that. Again, this is between again 0 and 1. And I do find out this one as the scattering power component utilizing the Kenyu matrix first element 2K11, as you have seen that before also. So this is the power component. So this is what I am utilizing. So I utilize the trihedral, dihedral, and the random volume. I found out the similarity measure for each one of them. I found out the normalized similarity for each one of them individually. And I found out the scattering powers corresponding to each one of them multiplied by the total power. I take this area, which is the San Francisco area of what is taken from AMERSIE. What do I see? I see when I try to find out the trihedral similarity. First, I try to understand if I'm able to understand, am I able to generate the similarity information or not? And if I see that similarity on trihedral, I see, yes, I'm able to compute the trihedral very well over the ocean area, very nicely. But if I go to the forest, in the urban area and so on, it's low, which is very obvious. It happens when I go to the dihedral over the area which is forest, which is water body, it's 0, almost close to 0. But it's high when I have the dihedral. So the similarity is nice with the dihedral. Similarly, over here in trihedral, here is a mixture again, because this random volume model, which is taken from the Freeman, is a very primitive model, which is able to capture certain things. Of course, it's able to take the information from here, but as you can see, it is also high, not so low in other areas also. Over ocean areas also, it's not very low, but it's also around like 0.6 around over here. So it's not low because, as I mentioned, it's a primitive, it's the most primitive model for volume. We just wanted to see just the first instant. You can also, of course, improve this. You can take any model, any volume model, and do the same thing over here. But the idea over here is to take the most simplistic and try to generate the clustering and see how are we able to generate it in a better way or not. And so we are able to see that we are able to see the similarity to a great extent for these type of targets. And then you are trying to see over certain areas. You see over this area, I compare it with the Freeman-Durden decomposition. You see the double bounce over here is much higher for the GD, the FDD, the Freeman-Durden is much higher. The volume is much less, which is obvious. In the area where I have, again, an urban area also over here, but it's a mixture over here, I also have this double bounce, much better than the Freeman. And of course, the volume is less. So the idea is that how do I do that? I took the PolSAR data, I compute for each pixel these values, the WA, WB, and WRV, and I compute for each pixel. I found them to be characterizing within a typical class of surface, volume, and double bounce. I arbitrarily clustered them within 30 clusters, and I merged this cluster depending upon the dominant preserving mechanism. And then I do the Wishart clustering within the cluster, and I just make them just a color them as such. So this is what, as you can see, this is this kind of a similar thing which has been done in the literature, but they have done with the Freeman-Durden decomposition. We have replaced that with the geodesic distance-based similarity measure scattering power, and the results are very clear. If you do this with the Freeman-Durden on the Wishart, you see this is the results. So we are just making them in this number of clusters. So you have just 5 for each one of them. And if you see, this is the GD Wishart for us. I'm able to capture better in the urban area. A closer look will reveal that, of course. If you see that on an urban area, it's not able to get that well for an urban area. With the GD Wishart, we are able to have much better. So that means I'm replacing the FD with the GD. The Wishart remains the same over here. Nothing changes in the classifier. I think that nothing changes as such. This is again with the similarity measure with the image from Mumbai. I will not go through the detail, but as it says the same thing. If you can see, this is the ocean area. It shows the same odd bounce better, the double bounce less. And in the urban area, it shows better the urban area. And if I see, this shows better again in terms of both not only the ocean, but also the urban area here in the ocean. It is also misclustered, I will say, in terms of dihedral because of roughness over here. Here I'm able to capture better the urban area, not only the urban area, but also the area coming from the ocean. I go to a different of PolSAR clustering, like say PolSAR clustering 2. And this is utilizing again the geodesic distance, but this is again utilizing the parameters which we have derived just in the few slides before in part 1, where I said that we have computed the alpha GD, which is the one which characterizes the scattering type parameter, and the PGD, which is characterized as the purity scattering parameter. And as you have seen that you have in literature, you have the alpha and the entropy. Here we have utilized these parameters, which is the alpha GD and the purity. And you are able to put them in, again, different clusters, again, 8 clusters over here. And you are able to, again, cluster this image into 8 different clusters over here. So as you can see that it is able to cluster very nicely the entire San Francisco image. This is the C-band image utilizing this PGD and the alpha GD. The branching over here, or you can see the groups over here, are considered taking into account the different kind of scattering models which are there in literature. So basically the one which has been taken by the Yamaguchi volume model, which as you have seen before takes these different criteria which depends on the ratio of the copole channel. So we have taken those as the demarcation from coming from these different constituents. So where it will be surface and from where to where you have volume. On the x-axis, which is the PGD, this is just a very trivial break between something which is less than 0.5 and greater than 0.5. Simple as that. There is only two versions, but this one, this taken from these scattering models which are there in literature, and we have formulated those scattering models in terms of the alpha GD to get what is the corresponding alpha GD for those scattering models in the framework of our scattering model, and those have been taken to be the discriminating zones as such. And if you see that, I'm able to well capture the clusters in this image. This is the area again of San Francisco with the ALOS. I'm getting a little bit different over here because I'm seeing different scattering because of the L band, and able to capture very nicely the entire urban area. This is also an urban area over here, and so on, so forth. I'm able to get very nice clustering from the area of Mumbai, where you have urban areas coming from here, and there are wetlands over here. You are able to capture the mango. There are some mangroves over here. This is the area where you have a thick forest. The water body is also very nice. Over here, there are many ships and trawlers also over there. So you are able to capture in a very nice way also the clusters of this image, utilizing this alpha GD and the PGD. This is an area which comes from the agriculture area, from a radar set to C-band data, where you have the crops are in different maturity stage, and different crops, of course. There are several different crops and different crops in different maturity level. So you are able to see again, they have been clustered depending upon what kind of maturity stage or phenological stages they are, and which type of crops they are, depending upon their individual scattering, depending upon again their structure. So you are able to again characterize them in terms of different clustering zones over here, the 8 for this agriculture area. Of course, as I said over here, this is the mountain area. You are able to get some clusters, but as I said, some of the effects are also from the topology over here. The other one, the next one is the radar built-up index. What you have in literature, in optical remote sensing, you have something which comes from the optical, from the multispectral data. You have something which corresponds to the built-up index, but there is nothing as such which is coming from a PolSAR, which characterizes built-up index. And this work we have tried to analyze, again utilizing this similar analogy, similar techniques, what I have been talking about till now, utilizing the framework of the unified framework. We are able to have something which is called the radar built-up index. What is the thing is that similarly over here, I have the information from the duration distance. I have all the mechanism over here. I do again the same thing. I do the design of the observed with all the elements over here. I take the similarity measure over here, and I do the dominant sorting. This is similar to what you have seen before also. Till here, we are good over here. Now, what is the built-up condition? The built-up condition is, from the literature, we know that the built-up, if we have the scattering coming from either a dihedral or a nanodihedral, or the two helixes. This is what is there in literature. We know that from the fact. So that the point is that, is my pixel belonging to any one of them in the dominancy? So that means I have the dominancy already sorted out. Then I'm trying to find out whether in the branching condition I have something coming from these or not. If they are coming from them, I mark them to be the built-up pixel. Otherwise, I don't say a built-up pixel. This is one way of doing it. Among the other, this is one way of putting the dominancy of the similarity to the target, which I know is contributing to the scattering from the urban area. Narrow dihedral, helix, both the helixes. The other one is something very simple. tell this as the RBUI, radar variation index. I compute the max over all of them, max over all the sorted over here, all of them which are unsorted over here. It's not sorted, but I find the max over here, and this max corresponds to this RBUI. I just threshold this RBUI. You can use any thresholding technique. You just use a thresholding technique, and depending upon the threshold, I put them to be as built-up index or non-built-up index, and that gives me quite a nice way of looking into things. But before I go to find out the built-up map, as I mentioned, let us try to look into and analyze the intermediate products, the products which actually tells me whether, well, the process which I'm doing are justified, fair or not. So I take the image of San Francisco, radar set 2, and I find out the built-up scattering dominancy one. That means I take the first 3 dominancy and I put them as R, red, green, and blue, and the black one is the dominancy beyond the 3. I don't care of them. So if you see, the dominancy corresponds to those scatterer actually comes from the urban area, which is very true. The other one are just black, so they are not coming from anywhere else. And this is the RBUI, the radar variation index. This is going from 0 to 1. So the max over all the similarity coming from the dihedral, the nanodihedral, and the 2 helixes, which actually gives me a good information that the higher it is, I'm able to capture more of the urban area. So this is the radar built-up index. I just do a thresholding, a simple thresholding of Otsu, whatever you want to do. This is up to you. And I just do a thresholding. This is by the dominancy mechanism, no thresholding. And this is by a thresholding method. So I just do a dominancy where there is no thresholding. I can also do something with a thresholding. So the results are more or less similar. Nothing much difference as can be seen with eyes. But yes, of some areas you can, of course, look into more details about the areas. But the interesting part is over here, you are able to capture this orthogonal oriented urban area also in the urban area, which was not possible if you use decomposition powers. That's what we have seen. If you just use decomposition powers and try to do a classification, supervised classification, you will be missing out this area. You have to do some more sophistication into that. But here is straightforward and simple, where you're taking only the dominancy sorting and able to capture the urban area, which are not only orthogonal, but also oriented. Similar things happen with the thresholding of the RBUI generated. The area coming from Kyoto, from Japan, this is an ALOS image. You can see this is, again, very nicely gives you the information about what is the built-up scattering dominancy. This is the RBUI, captures very well the urban area over here and a small portion over here. If I just try to see again the dominancy-based method, I'm able to capture very well the urban area, and also similarly for the thresholding method for them. I go to the one with ALOS 2 with the Mumbai area. The urban area quite well picked up by the dominancy, quite well done by the RBUI index. You are able to get again the dominancy sorting by the method 1 and by the method 2, which is the RBUI. Again, as you said, similar in the sense, but yeah, if you want to go into more details of understanding each and every areas and so on, the ground truth, yes, so some of the ground truths we have, but if I want to go to detail, you will be able to understand more of there's a variations or not, but we have seen that with also ground truth in the article which is mentioned, you are able to understand how they behave or what are the differences when you have it. I just do it over some areas where just to show you how they are with just one method. This is the area of a UAV SAR L-band. This is the built-up scattering dominancy map, and I see it that you are able to capture most of the urban area within the 3 scattering mechanisms. I just do a dominancy sorting. I don't go to the thresholding. I just do a dominancy sorting, and I'm able to capture more or less the urban area which are there in this area. The next one is an ALOS image, which is taken over Pavia image. This is the dominancy scattering map over here, and again, if I try to do the dominancy sorting method 1, I'm able to get the information from the area which are urbanized. Yeah. So this talks about the RBUI, the Realization Index. Again, as I mentioned, utilizing the same framework of the geodesic-based analysis, the geometry-based analysis, I would say, and also the unified approach which we have introduced to find out the radar urban index, and you are able to capture information about the urban area, not only in terms of the final map, but also in terms of the intermediate information, which talks about the priority of the dominancy mechanism happening. From here, I move to the next index, which is very important, is what is called the radar vegetation index. There is a radar vegetation index, which is there in literature called the RVI. It gives the information about, of course, the radar vegetation index characterizes the amount of randomness when you have vegetation. So it's actually a measure of randomness, you can say, but it's just that it's scaled in a different way. I mean, it's a index which can also be equated to entropy, pedestal height, or any other kind of mechanism descriptors which you can think, but well, you have a difference in the scaling. And that's what makes it much more useful to characterize certain kinds of target. In this case, it is vegetation. Going from that analogy, we made something which is called as the radar vegetation index, but there is a G in front where it is called the generalized radar vegetation index. Now, how is the generalized form comes into picture? So we have done our study over the area, which we have a lot of collaboration with Canada over the Manitoba test site, which is a part of the JCAM mission and so on. And we are interested in finding out several agricultural applications, starting from crop phenology estimation to biophysical parameter estimation to classification and so on, and ultimately giving at the end an ARD product and so on. But well, this is a kind of research components which are there as a part of the project. I will not go into all of the details, but just to try to say how are we utilizing the generalized volume scattering, generalized radar vegetation index in the context of this work. So what is this GRVI is? Again, as I said, I will be again keeping my same thing within the Kano domain, the real 4x4 Kano matrix. The real 4x4 Kano matrix can be written in terms of the elements of the scattering of the coherency matrix like this. It's simple to formulate. It's not difficult at all. You can see the diagonal elements are just a combination of different components of the diagonal element of the coherency matrix, and the off diagonals are nothing but the real and imaginary part of them. This is the Kano matrix representation for a coherency matrix, and there exists a generalized model, a generalized volume scattering model introduced in this paper, which is there below, which generalizes all the volume scattering model, and which has been used a lot in literature for many different kinds of applications and also in decomposition methods. We utilize the same generalized volume scattering model in the framework of the Kano. So it's nothing, but it's just the Kano framework. And we just assume something, which is the rho parameter. We assume that is a correlation between the HH and the VV. We just take it to be as 1/3, and it's there in literature. So it's just, this one is taken to be as a constant, is 1/3, but otherwise it varies, as you can see, as a ratio of the co and the copoles. So this is the gamma parameter, which controls this generalized volumes scattering model. And this is what we'll be utilizing. So this is actually comes from the data. So you can say that the gamma is a data driven over here. Now, how do I formulate this? The vegetation index. So the vegetation index is given as this. The GRVI is nothing but a parameter beta multiplied by FV. And this varies from, the GRVI varies from 0 to 1, which we want because it's an index which should vary from 0 to 1. How, what is it? What are these two parameters, beta and FB? Let's try to see. Beta is this parameter. It is nothing but 1 minus GD, the similarity between the observed and the geodesic distance between the observed and the generalized random volume case similarity measure. And beta is nothing but a parameter which says P by Q to the power twice of the GD. What is this P by Q is? The P is nothing but the minimum of all the geodesic distance between the observed and all this elementary scattering. The trihedral, the cylinder, the narrow-dihedral, and the dihedral and narrow-dihedral. So I do the mean of that and the max of that. And I divide them between this, the mean and the max. This is something which is kind of modulating this information, because this is what you desire. But it is not, as we have seen, that even if you use the generalized scattering, volume scattering model, the GD is generalized, as I said. So I need something to modulate that factor. And this is the modulating factor. And as you can see, that we are able to get these two extremes. When you have the GRVI equal to 0, when I have the observed Kanu matrix corresponding to any one of them, any one of those elementary target. That means, of course, there is no randomness. These are all coherent, which means my generalized radar weightation index should be 0, because it should characterize a randomness as such, because it's a weightation index. When I have K equal to KV, then I have the GRVI equal to 1. That means when I have a perfect volume scattering model, I am able to get it to be as 1. Otherwise, I have in between all the 0 to 1. So it characterizes that. How do I see that? I see a temporal image. I see a temporal image over this area, which we have the SMAP-BEX mission of 16 in Manitoba. I'm able to see from the dates from May to August. I'm seeing the phenological changes of the crops and how the randomness increases. And this parameter is able to capture nicely these growth stages. So over here, the fields were bare, mostly bare, but you see with time it is maturing the crops and matured, and then you have some of them as harvested and so on. Some of them are still there, some of them are harvested. So you are able to see in a movie as such. You can see that how they are evolving with time. So this is the area where you have 5 different kinds of crops, different structural properties and so on. But my parameter, the GRVI, is able to capture very nicely the stages in which the changes are happening, because I am taking the generalized volume scattering model and I am able to look into this, how it's happening. Let's see how it is different from the RVI. If I see them over here, I see this is the temporal series of the area which is from the Vijayawada area in India. This is the area where we have a lot of rice crops. We don't have anything over here. These 2 areas are the rice fields. Here I don't have any rice grown. It's coming up. It came up over here, still not over here. Here it has come up over here. It's still rice over here. So as you can see the temporal increase of this area where I have rice. The RVI, I am not able to capture it, even if there is rice has come, but you see the GRVI, it's able to capture the information as soon as I have the rice coming up. You see the next one. I have full grown rice. The RVI is still not able to capture it. There's a problem over here. But over here with the generalized volume case and the GRVI, I'm able to capture very well the growth stages. It comes over here. Here it is able to capture, but here it is harvested already. So it's the bare land with some kind of a roughness. It's able to capture over here, but not when the rice was there. The standing rice was there. So I'm able to capture that. You can see that very well in different kinds of crops. This is a different kinds of crop, direct seeded and transplanted. I'll not go into the detail of that, but we are able to look into the temporal series, the temporal variation of these parameters over RVI, the conventional one which is there, and we are able to get much more better information in terms of them. We are able to do the retrieval of biophysical parameter, and as you can see, I'm able to get quite better retrieval accuracies in terms of the R values of the re-rise for one type, the TR, the transplanted one, compared with the RVI. The same thing happened with another type of rice. I'm able to get much better when I compare with the RVI. So in this case, I'm able to get better off. When I compare them with the estimated parameter, the estimated PAI with this, the regression, I do the estimated PI with the RVI. You are able to get much better with the GRVI and see the R values, they are all much better than utilizing the RVI. How do I see that? I can see them also in terms of this. If I see how it has matured, for example, when I have no rice crop coming up, and if I have the fully grown stages and I utilize my alpha GD, I'm able to characterize, I'm seeing the differences. Here I'm able to see scattering which are coming from the surface light, which is true. Here it is all water, it is all watered field over here, as you can see, watered or bare field. Here, when I have the information coming from the fully grown rice, I am able to get information which is coming over here. It's not dihedral as such, but it's again a mixture towards dihedral, but a mixture coming from dihedral, but also other kind of scattering which is there inside the canopy. If I try to utilize the PGD, I am trying to see more purity over here, as you have seen before. But as I see, when the rice comes up over here, my purity decreases, which is obvious because my GRVI increases. Helicity, of course, give me information. Contrasting, of course, here helicity is very poor, I mean very less, which is true because it's symmetric. No scattering, bare, random, bare field, and so on. High, low value of alpha, very high value of PGD. So hence, of course, you will expect that your tau will be also be less. Here, you are able to see slightly higher tau than compared to this one. If I do the segmentation, as you have seen before, well, I'm able to segment very clearly when I have only over here bare. This is the urban area. As you can see, that's the top portion is cut out over here. This is the area. This is the Vijayawada city area. This is a city, but only a portion of it has come in this acquisition. So this is the city area over here. This is comes in this cluster. Over this cluster, if you see, it's over here, it corresponds to these two cluster over here where I have very low alpha and low PGD, high PGD value, sorry, high PGD and low alpha over here correspond to this cluster. Here, you corresponds to slightly higher alpha, around 60 degrees, and also lower PGD, less than 0.5. You characterize it in these scattering zones over here. So you can see the diversity, how you're able to do that in terms of the segmentation. How does it look in terms of power? Dominant scattering type. So again, as the same thing over here, it's an intermediate product to look into the contribution of the dominancy. The dominancy over here, of course, as we have seen, is odd bounds, which is pretty clear when we have the alpha GD to be very low. Here, as we have seen, it is even bounds, but of course, a mixture, of course, of even, a little bit of odd, because it is, as you have seen, the alpha GD was not towards 90 degree, because that would have been pure dihedral, but it is somewhere around 60, something around that. So there is a mixture of dihedral, majority of dihedral, but something inside that also. So that can be seen over here. It's not, it's even, but you have a mixture over here. If I see the powers, and it is see that, of course, the powers over here are, of course, here it is surface line, which is again true because your alpha GD was low, purity was high over here. You had the dominancy to be as surface like, and of course, then the PS power is also very high. Here is the urban area. If you go into this area where you have more of the crop grown over here, as you have seen over here, the alpha GD was high towards 60 degree. The combination was, it was even bounds, but there was some kind of a mixture of other scattering, not pure dihedral, of course, not. But it was a mixture of majority of dihedral, of majority of even bounces, but also mixture of them. So you can see there is a combination of PD and PS. So it's a little bit not red as such, but a kind of a magenta color. So there is not totally a dihedral kind of thing, but a combination as we have seen before. And also we have seen that with the the mixture of the scattering. So this is what I have with the applications, and so I end my talk with the summary that we have seen that there is a flexibility of utilizing the PolSAR data representation, both in terms of the complex, starting from the complex 2x2 scattering matrices, the 3x3 complex covariance structure, but also you can utilize the Kenu structure, which is the 4x4 real structure, and it is equivalent, of course, for both of them, both for coherent and incoherent, the 4x4. Everything what we have talked about is, of course, based on the scattering physics-based approach, and this is what you have seen in your earlier lecture yesterday on the physical scattering information extraction. It's the same over here, but what we have seen is how the mathematics is there, or the algorithms are developed within keeping in mind the very fundamental physics of scattering, and utilizing them we have developed different kinds of methodologies. We have also looked into the methodologies which are there in literature. They are so powerful and they are so elegant, but all of them utilizes the basic fundamental physics approach. We have seen the differences, and also the way you can handle the coherent and the incoherent scattering mechanism, which is very important to understand. We have seen the coherent and incoherent decomposition principles. Of course, these have different ways of, again, handling the data, where you have a 2x2 complex matrix, or a 3x3 covariance structure, or a 4x4 real structure. We have seen how we are able to handle them. We have seen a unified framework which encompasses not only finding out the scattering mechanism, types, purity, and helicity, and so on, the descriptors, I would say, the polarimetric descriptors, but also the powers associated with with them. We are also able to find out the hierarchy in the scattering, which is very important. So all the intermediate steps are also we are able to capture, which also plays a very, very important role when you are trying to understand each and every mechanism. We have also seen this model-free approach, which characterizes taking information given from the work of Hoynen, which characterizes the scattering in terms of regular and irregular. We have borrowed a parameter which is coming from an optical polarimetry, ellipsometry, the scattering, the degree of polarization from the Barakat, and which is utilized in combination with the elements of the coherency matrix to find out the model-free approaches. And then we have utilized them to see some of the applications for Earth observation, change analysis, clustering, urban, and agriculture. What we can do more from here is that we can extend this methodology. We have already extended this methodology for this model-free for compact. There is already a publication. You can have a look. We can also go into the dual pole mode and any other modes which you can think of, and because this, as I mentioned, that this is equivalence in the way that how you can move from the quad pole to a compact, the dual copole, and possibly also to the bistatic mode. All these approaches, all these indices, or all these descriptors which we have used, we have utilized for Earth observation, and that's what I've shown over here. But it can also be extended for planetary observations, and since we have many missions which will have fully polarimetric dual frequency SAR data for the analysis of the moon. We have from India, we have the Chandrayaan-2 already in orbit, and the data is already giving. We have the S and the L bands. It's a dual frequency fully polarimetric SAR data, and it is giving beautiful information, beautiful data. All this what we have discussed today for the Earth observation context can be extended very nicely for the analysis for the planetary observation. So I end my talk over here, and thanks to all the people who are a part of this collaborations, and the collaboration continues from here onwards, and we are still collaborating with many, many more coming up. Thank you very much for your patience and listening. I think I am within the time frame, Andre.
Yeah, more or less. It's okay. But thank you very much for this outstanding talk. It was impressive. I mean, truly impressive. And I think that we have a couple of questions for you in the Q&A box. Yeah, the first question is a bit generic. I mean, pretty wide range, in the sense that there are some doubts about the compact ball. So it's pretty wide.
Okay.
Pretty wide argument.
Okay, so just to give you an idea that what we are doing is we are just projecting, let's say, the full polarimetric information. If you have the S matrix, you are projecting only on the R, and so it's only RH and RV. So you are only have the RH and the RV. You have the complex. That means you are transmitting a circularly polarized wave, and you are measuring only the the H and the V. So what you have the information is the circular transmit and the linear receive. What you can also have is a circular transmit and also a circular receive also. So these are the different modes. What you have is you do not have the full polarimetric information. You have the half polarimetric information, you can say. But what you are gaining for them is that you have a wide swath in that, because you are just playing around with the pulse repetition frequency. So it's a new way of information extraction. There are the RCM is already in space. I'm sure it's giving the data. I'm not sure it is free or not, but you are able to get information from the RCM. There are other satellites which were there as RISAT from India, which has unfortunately stopped working, but the data are available in the compact fold mode in RH and RV. The sending is a right circular, and you're receiving it in an H and a V. So that's the compact polarimetric. So you can utilize this compact polarimetric information in terms of the Stokes vector representation, and then that can be used to find out as I mentioned, but I do not go into that, the different kind of decomposition. So it's, I would say, a different talk already, and I don't have the time to talk about entirely for that. Some other time, I would be very happy to go into the details of compact polarimetry.
Sure. Thank you very much, Avik, for this explanation. And there is another question here that is about, I mean, I read it. The result obtained from C-band RADARSAT-2 and L-band ALOS-2 shows slightly different. Is there any explanation?
Which example can you talking about? Can we, for all the examples? I mean, if I'm assuming you are talking about all the examples where I have the RS2 and the ALOS, well, I'm assuming that you are mentioning all the results, the differences. Assuming that it is, I would say there are two differences which I can think of, and which we have seen, is that, of course, one is the change of the wavelength. So one is a longer wavelength than the other. And also there is a difference in the incidence angle also. There is a difference in incidence angle for the two acquisitions, slightly different. So that will, of course, cause a difference in the scattering mechanism for the different kind of targets we are looking around. For example, in the urban area, as I mentioned, so the urban area where we looked at in the San Francisco area, for the Mumbai area, as I can tell you that this urban area is quite complex in nature. It's not like the orthogonality is not directly there. So it's not like a dihedral kind of a true. So it's a kind of a mixture. And in this kind of a mixture, you have the penetration capability, but since you have kind of a difference in the wavelength, there is a penetration differences when it comes from directly the urban area thing. And also there is a also scattering from the vegetations kind of within the urban area. So this kind of changes this information content. And also, as I mentioned, there's a slightly change in the incidence angle also. So this possibly could be the reason, as I can think of over here, is the difference in the of the results.